Okay, hello everyone and welcome. My name is Liad Magen. With me today is Sarah here.
Hi everyone, my name is Sarah Cepeda and welcome to the Meetup NeurIPS Austria.
And we're very excited. We have 10 researchers that are going to present their work from NeurIPS 2021. We are going to start with Mathias Lechner from IST. Also, please feel free to write your questions in the chat. Okay, Mathias.
Okay, thanks. Yeah. Hello and welcome to the presentation of our paper, Infinite Time Horizon Safety of Bayesian Neural Networks. And this is a joint paper together with George Shikelic, Krishnendu Chatterjee, and my supervisor, Thomas Hensinger, all from IST Austria. We start with, this paper is about safety verification of neural networks, and safety critical applications usually require some formal guarantees about the correctness or safety is always satisfied in the system. So for instance, like robotics, robotics or healthcare systems usually have constraints on the safety of the system. And we are particularly interested
Mathias, is that only me that not seeing your screen? We don't. Can you please share again?
Okay, sorry. Safety is always
Mathias?
the system. Yes. For instance, like
can you hear me?
Yes. Robotics or healthcare systems
we
usually have
are not seeing your screen.
on the
I think
system.
you know.
Now it's okay.
And can you see it?
Yes, now it's okay. I see it.
Okay, so I can continue? Or is it
yes,
still?
yes, please go ahead.
Okay. Yeah, this we are interested in one particular type of neural networks, in particular Bayesian neural networks, which have weights as random variables are weights, and this gives them the networks the property to learn arbitrary distributions of the output. And yeah, as we see here, an example of the Gaussians weight distributions on the weights, and then we have a posterior on the output neuron that looks much more complicated. And yeah, this way then the network can learn also uncertainty instead of just a single prediction, an entire distribution of predictions. And we focus on a particular type with ReLU activation and Gaussian bias, as already mentioned, because this is the most typical setting for Bayesian networks. And in existing work on Bayesian neural network verification has used sampling-based approaches, and they have some downsides. In particular, they only provide statistical guarantees on the safety. And in closed-loop systems, sampling gives only the guarantee over a finite and bounded time horizon, because we can simulate the system only to up to a certain time bound, right? And then we need to stop simulating. We cannot prove that the system is forever safe. And one particular aspect of Bayesian neural networks makes this safety verification question in particular interesting, and that is that Bayesian neural networks are unsafe by default. And that's because the weight priors usually have unbounded support. For instance, the Gaussians have unbounded support, so assigning any probability to tail events. And as a result, the posterior also is very likely, not guaranteed, but very likely to have also unbounded support. So assigning a positive probability to any output event. And this is essentially contradicting the definition of safety, which says that no bad action should be produced by the network in certain conditions. And we solve this problem by introducing safe weight sets and make the Bayesian neural networks only sample from the safe weight sets instead of just this arbitrary prior distributions. And we do this efficiently for Gaussians by parameterizing our safe weight set as a product of intervals around the mean. So essentially expanding around the mean with some epsilon. that is guaranteed to be safe, and then we can sample on the network on this set. And we have two particular sub-problems or type of problems. One is for feed-forward. So we have just input and output constraints specification given, and we want, like, the safety is given as an input and output constraint, and we want to check if the network violates them. And the second problem considers closed loop systems, where we have a Bayesian neural network as a policy interacting with a system. And this closed loop system runs forever. So infinite time horizon systems. And our method essentially then recalibrates the Bayesian neural network on these safe weight sets to ensure safety. For instance, here we see an example of if we basically narrow down the weight distributions, also the posterior changes, and these tail events that we say are unsafe get removed from the posterior. We start with the problem for feed-forward specification, and then go to the closed loop setting, because the closed loop setting requires some techniques from the feed-forward safety problem. So we have essentially the feed-forward problem is that we have given an input set and an output unsafe set as just inequalities on these variables on the input and output. And we show in the paper that essentially this problem can be reduced to mixed integer linear programming or SMT solving. Essentially, there has been done existing work for deterministic neural networks that also reduce to mixed integer programming. And we basically extend the approach, but this time we treat the weight values as a set, as an interval, as this product of intervals, essentially for the entire network. And so this essentially can be reduced to BIP solving. The second contribution is that we show for closed loop systems of how to verify safety, and in particular for infinite time horizon, so that the network runs unbounded for unbounded time. And we have given the specification as an initial set x0, which is where the system starts, and a set of unsafe states x0 that the network should never, that the system should never reach. And we use one technique from control theory called positive invariance, which is a set that satisfies these three conditions. First, that the initial set is contained. The second is that it doesn't intersect with the unsafe states, and the last is the closeness condition, which means that if we are in the invariant set and the network and the system performs one time evolution, we are again contained in the positive invariant. So this has been established already in control theory, and used for verification there. And what we do essentially, because this set is potentially infinitely large, that we represent this set as a deterministic neural network, and we treat the inclusion of the set as a binary classification problem. So we have essentially this invariant, this potentially infinite set represented as a binary classifier neural network. And then how to obtain, how to make sure that this network satisfies the three conditions that we proposed, that we showed before. We make use of a learner verifier framework, where the learner tries to train the network to satisfy the invariant condition, and then we put it into this mixed integer programming solver, as seen in the as we have basically can reduce this, as we'll show how to reduce this to the problem type 1 that we had with the feed-forward setting. And essentially, the learner is composed of two losses that basically makes the system satisfy the invariant conditions. For the one is the specification from the initial states and the unsafe states, the first two conditions. The second loss is derived from the closeness condition, that if you perform an update, the system should also be inside the invariant. And then essentially all three conditions can be reduced to the problem type 1 that we have shown before, which is essentially mixed integer programming, and where you can check if the system, the invariant satisfy or values the condition. And in case the conditions are violated, we make an update. We retrain the network with this counterexample that has been found by the constraint solving step. And this process of a learner verifier is repeated until a true invariant is found. So if the MIP or constraint solving step says that the positive invariant network satisfy all three conditions of the positive invariant, we can conclude that the system is safe, as we prove in the paper. This can be adapted to safe exploration reinforcement learning, because as we know, reinforcement learning requires some randomized actions, and we could use the Bayesian neural network to sample these randomized actions by essentially sampling only from the safe weight sets. That ensures that the system stays safe during exploration. And also, we can use the safe weight set potentially for gradient descent, in particular projected gradient descent, where if the parameters of the network land outside after a gradient update are outside of the safe weight sets, we essentially project them back into this safe weight set, and ensure that the system stays safe also during after the learning phase or during the learning process. Details can be found in the paper. So also we performed some experiments to validate whether this works in practice, and we used the inverted pendulum task and the two other tasks, collision avoidance, a linear system. Here we have seen the inverted pendulum, and by sampling we can plot the vector field of how the system evolves when we have the two variables x and y of the system. And with green and red, we show if it's empirical estimates or a sample basically tell if we just use sampling instead of our tool, if the system is safe or not, and to show red and green. And then we try to learn the invariant, and after the first learning iteration, we get like this kind of decision boundary, orange and green, with green being inside the safe, the positive invariant. And we have found a counterexample after we pass this to the verifier step. And this process is repeated with additional counterexamples found until finally, after 5 iterations, the verification step concludes that the system is safe indeed. And this, what I forgot to mention is that all this, we need to learn an invariant for a fixed safe weight set. But we can actually, if we want to compute as large as possible safe weight set, we can essentially, instead of starting from scratch every time we learn the positive invariant, we can just use the one to incrementally enlarge the safe weight set. And this has been done here, where essentially we try to enlarge the safe weight set by using the standard deviation of the weight distributions around the means. And for this kind of type of networks with different techniques enabled and disabled in our algorithms, we could obtain reasonable bounds on the safe weight set. So essentially, the safe weight set is large enough to still make the Bayesian neural network behave as a probability distribution instead of just a deterministic network if the safe weight set is too small. So in conclusion, we have looked at a new perspective on the verification problem of Bayesian neural networks by considering sure safety and safe weight sets. We have shown that the feed-forward safe weight set computation can be reduced to constraint solving. And for closed loop systems with Bayesian neural network policies, we have introduced a learner verifier framework to learn positive invariants and basically use the feed-forward reduction to constraint solving as a step in the entire process. And also, we have shown experimentally that the system, that the algorithm works in practice on small but kind of standard benchmarks. And finally, the code is available online. So, thanks.
Many thanks, Mathias, for the first talk. I would like to invite the attendees to post their comments. We have identified a little bit of delay between the live streaming on YouTube and the talks that we're presenting. So feel free to post your comments while our speakers are presenting their work. Liet, I don't know if you have a question for Mathias.
Yeah, I do have a small question, Matthias. Is the Bayesian neural network, in terms of the reinforcement learning, is it only for binary, so only for 2 actions, or can it be also extended for multiple different actions, to choose between multiple amounts?
Yeah, it can essentially be adapted to an arbitrary number of output variables. Just we showed in the illustration just with a single output,
okay,
just to visualize it better. But essentially, it works for arbitrary outputs. Yeah, we have some of our experiments consider also multiple outputs. Essentially, that we learn basically uncertainty bounds or uncertainty distributions of each prediction.
okay.
This prediction could be arbitrary, essentially.
Until I see additional questions from the viewers, I have another one. You were talking before also about setting the weights, the safe weight sets, and this is actually come from the data. So you need to look at if I understood correctly, you need to look at the median or the standard deviation of the data, and according to this, you decide or define what the safe weight sets is, right?
Not at the data, but the means of the weight distribution. Because if I go back and show like the networks here, you learn essentially the means of the Gaussian weight distributions, also the standard deviation to some degree. So instead of just you can think of the normal weights of a deterministic network are now the mean of a distribution, right? And the safe weight sets are a set around an interval around the mean of the weight, essentially. So it's kind of learned from the data, but it's not the mean of the data itself, but it's basically learned through the training process of the Bayesian neural network.
Ah, okay. Thanks for this clarification. I still don't see any questions coming in the chat. So I will also use this opportunity to say that our next meetup is planned on the topic of Bayesian neural networks. We have two events coming up about this. The first one is going to be a lecture, a talk from a researcher in the field, and the second one will be a seminar where we discuss this field further. And so again, please post your questions on the chat. And if there are no, then Matthias, you have a second paper that was accepted to NeurIPS.
Yeah. 1 second. Let me just switch content.
Oh, Matthias, I think there's. Oh no. Okay. Yes, there is a second question. If it's okay with you.
Yeah.
Elias, do you want to ask it yourself?
Yes, I mean, I wasn't sure if I should just jump into the call, but my question was regarding the ILP solving. Like, how does that scale in terms of like the number of network weights? Can you do that for hundreds, thousands, millions?
That's actually a very good question, and yeah, you can it depends on if you do with the feed forward or in the closed loop system, because checking actually the invariant conditions is a bit more difficult, where you scale usually to only a few hundred, but in the feed forward setting you could scale to multiple hundreds to 1,000, but still multiple orders of magnitude away from big vision networks. In terms of scalability at the moment.
Okay, thanks.
Okay, so we continue with your second paper.
Yes, the second paper is called Causal Navigation by Continuous Time Neural Networks, and work has been done by Charles Forbach, Ramin Hasani, Alexandra Amini, myself, and Daniela Rus. And the presentation was originally done by Ramin, but I will take over his part in explaining our work. So here we have given a sample task of a network that performs autonomous driving. So it observes from a camera the road, and it outputs the curvature of the road. So essentially the steering wheel, the target steering wheel. And what we want to know is like if the network, where does the network look at? Like, has it learned really a true the relationship between the pixels and the actual task? Has this been captured or not? And there has been one method called visual backprop and among other methods for computing a saliency map, which helps us visualize essentially where the network is looking at. And here we have 4 different types of networks: as convolutional neural network, continuous time recurrent neural network, an LSTM, and a neural circuit policy. And what we see is that we get vastly different results in terms of where the network is attending its visual focus. So in particular for the convolutional neural network on the left-hand side, we see that the network seems to be looking at the grasses and the bushes to really determine where the street is. So this is not really nice, because we want actually the network to capture the road instead of just their surroundings and making a decision of where to drive based on things outside of the road. And so what we actually want to do is to learn a better causal structure of the task, because this has been shown that to not really work well in this autonomous driving setting, where the network attends to surroundings. And learning a causal structure really of the task. So what variables influence which other variables has been there has been a lot of research done in this area, and combining this with machine learning, most dominantly by Werner Zellinger. And there has been established some taxonomy of different, like essentially a hierarchy of different methods. And the most important aspect here is really the physical models, which are derived from equations. You can think of if you model a system, a pendulum or something like this, and you just apply Newton's law of energy conservation and apply what forces apply to which point, you kind of get a model that's really captures really the structure of the task really well, right? But this would work nice. But for certain tasks, such as autonomous driving, where you have given the input as an image, right? Where this physical writing down the equations is like impossible. But statistical models, like essentially machine learning, deep neural networks, have been shown to solve this task, like despite learning some suboptimal causal structure. And the question is, how can we really like combine these two things? Like when we want to learn something that has a nice structure, causal structure, but it's also learnable in an efficient way. And Werner Zellinger in his work discusses differential equations, which basically model physical phenomenon quite efficiently, and how a system evolves in time by essentially characterizing the rate of change, instead of the exact instead of the exact time of evolution. And enhances our understanding of really the physical of what's actually going on, like with these methods. Essentially, like here we just say that this work from Werner Zellinger essentially says that what is a differential equation, right? We define the dynamics of the system by the rate of change instead of the particular function, and then we have some uniqueness condition that the solution exists, etc. On this, and it kind of captures the causal structure of physical processes, right? Think of physics, mechanics, and so on. And because they can capture this so well, people have tried to use neural networks to parameterize this function. in terms of continuous time neural networks or ordinary differential ordinary differential equations, which try to really capture the benefits of this, because most data is generated by some physical processes. And so we try with this type of models, we want to get the benefit of this physical modeling, but at the same time want to have it learnable, right? Because in this example with the pixels that driving, where you cannot really write down the equations explicitly, we need to learn them on a larger scale. And it just dissects this neural ODE into input, hidden state, the previous hidden state, and the nonlinear function with a parameterized system. And in particular, this work on ODE networks, on ordinary differential equation, neural ordinary differential equations have been shown that this actually can be learned in practice reasonably well. And one other work from literature talks about dynamical causal models, which also from control theory perspective, which have a certain type of structure. They presented essentially as a bilinear approximation of an arbitrary nonlinear system, and are composed of some internal coupling, some internal interventions, and some external interventions. And they have been shown to this is everything on the slide is related work or literature from other people. They have been shown to really capture the dynamics and the causality of graphs and models in an ODE form quite well, at least for certain types of physical modeling tasks. And one type of network, the problem with the dynamical causal models is that they are still rather difficult to learn, and the capacity is quite small in terms of learnability. So what we did in previous work was to propose liquid time constant networks, which essentially take this leaky integrator ordinary differential equation model that has been used for modeling neurons in some smaller animals, and Huxley model, etc., and really use this model for machine learning, large-scale machine learning, and by simplifying certain parts. And so this is all like related work and existing work. But in this paper, we showed that this type of networks that we proposed before, like liquid time neural networks, are a particular type of dynamical causal model. So they essentially also fall into the same category as we shown before with this internal coupling, internal interventions, and the external interventions, more complex though. But essentially what the results here show, obtained by Ramin, is that they capture a lot of the nice properties that the control theory community has observed in these dynamical causal models. With minor changes that we see. Particular like non-linearities where before just a linear mapping had been before. And yes, so the experimental part of this paper, then we tried to solve a drone navigation task, and essentially the objective is to follow the red object that we see on the center on the left-hand picture, and perform also the where the model is attending the visual backdrop attention map. And we did again a study like on how different networks tend to learn this structure and where they basically attend their focus on. And again, like these liquid time networks in the form of these neural circuit policies have been shown to like attend the focus on the target actually best compared to other models which essentially start to overfit on the training data instead of really attending to the target, to the task. yeah, here we see an example scenario that has been tested. The network needs to, from pixel inputs, navigate the drone to the object. Yeah, we have also tested like training on just following, static navigation, and then testing on follow leader, so where the object moves around, essentially chasing around the target, and did some out of distribution test. So when we train on standard conditions, sun, daylight, etc., and then test the networks with fog, rain, etc. And we see that indeed these LTC networks, these liquid time constant networks, seem to capture this physical task of drone navigation, which is essentially like some physical process which can be captured nicely with these dynamical differential equations, and it works best on this particular task. So the takeaway is really that they seem that this liquid time constant networks seem to capture the structure best on this physical modeling task. And essentially when you capture better causal structure, you definitely generalize better to unseen settings such as this chase, fog, rain, etc., and also do the chasing target instead of static target. And also with respect to vastness to like rain, etc., perturbations. Thank you. As again, like this was essentially Ramin's work together with Charles, and I and Alexandra Mini helped with making this work possible, and supervised by Daniela Rus. Thanks.
Well, thank you very much, Matthias. I must say it was very impressive. This way that you really improved the results in sometimes even in 40% in the results. This is really, really impressive. We have some questions. So Bernard Lehner asks, what is the environment which you trained for the drones? It looks quite real, but he assumes that it's actually a simulator.
It's a simulator. I'm not sure which.
It's an AirSim simulator.
AirSim. Thanks, Ron.
Microsoft AirSim. Sorry.
This one. Yeah, so it's a simulator. The other question or comments?
Oh, well, Riad, if I can, if there is no other questions, I had a question about when the objective is static and it's moving, why do you think it performs better when the drone has to chase it?
Performs better. Maybe Ramin.
Yeah, I didn't understand your question, Sarah.
Well, it looks from this table that when the object is moving, it has to chase, and the algorithm performs better, right?
Mm-hmm.
Than when it's static. And I was wondering if you would have an idea why.
I still didn't get your question.
I think it seems that the general accuracies on the chasing task seem to be higher than for a static task. So
I see. Why this is the case? Yeah. So the reason is because the object is actually pretty close to the drone. Like the moving object is pretty close to the drone, but whereas like in the static target finding, the target is like pretty far away. So that's the difference. So when the target is like pretty close, then I mean there are some videos on the supplementary materials of the paper that you can actually see how the chasing task was structured, and you can see that we have the kind of target so very close to the field of view of the drone, and that's the reason why generally they perform better. But as we increase the time horizon required for performing these tasks, like for example hiking tasks, you see that the other models are basically failing if you do 50 runs. And hiking is basically in the forest. What happens is that you have some markers. Imagine you hike in the forest. There, you saw that those lines on the on trees, and you want to just follow those lines until you reach the target space that you want to arrive at. So it's like a longer finding target and actually moving towards it task. And then we see in the hiking that we can get some success from these NCPs. And remember that the entire tasks were trained offline and they were tested online. Okay. So the difference here is that like the task was imitation learning. So if you get any sort of success in these kind of things from imitation learning agents, that would be really, really beneficial. But this is just the beginning of the process. So we are working on improving also on these avenues, because still we need to get into the higher percentages in terms of performance.
Thank you. We have also another question. I don't know, Hamid, if you would like to say the question yourself.
Okay, can you hear me?
Yes.
Yeah.
All right. Okay, very interesting work, guys. Thanks for sharing. My question was, since you are building on causality, have you done any comparison to some other causal representation learning methods to see, in terms of capturing the causal factors of your environment, how well are you doing compared to some other benchmarks?
Yeah, that's a good point. So yeah, in the follow-up work we're doing that, but keep in mind that causality we're generally like studied in open loop problems, like for classification problems. For example, if you look into the literature, you'll see a lot of work on like capturing the causal structure of tasks and classification problems, especially more theoretical works. For example, there is the work on recurrent independent mechanisms. And that's something that we are thinking about benchmarking against next, to see what kind of independent mechanisms are learned. And
Cool.
In general, yeah, that's something. But in this work, what we wanted to really stress on is just focusing on these ODE systems and saying like there are certain type of ODEs or certain representations of ODE neural network that can capture causality, and some of them cannot.
Right. I could see this work fits very well in, besides something like recurrent causal mechanisms and these new modular models, right?
Right.
But
right.
mostly from the OD perspective. Yeah, thank you.
Thank you, Matthias. Before Ramin, you are basically the next speaker, but I guess before or while you prepare your talk, we have another question from Werner Zellinger about this table, and he asked basically why the light rain had so much better results. Is it because of the augmentation that you used, like in similar conditions, or was it, or you only trained with a clear weather condition?
What was the what is better? I didn't get what exactly is better.
It's in the table that Matthias showed before. That
Yeah.
the light rain always had like a very crazy accuracy, like 80%, 70%.
Oh, light train.
Yeah.
Yeah, I mean that's could be a simulator artifact, or could be the noise profile, you know, because this is not tested in real world. So like we really don't know. Like that could be like just the profile of the pixels would be better understandable for the neural network somehow, because the simulator, like for rain and the other conditions, are not super accurate. Still, it's photorealistic, but it's not perfect.
Okay, thank you very much. Thank you, Matthias, as well. Really amazing work, and guys should be proud of this. It's a really amazing achievement. Ramin, you have another paper that was also accepted to NeurIPS about sparse flows.
Yes. So let me share my screen. All right. So let's have to. Okay. So what is this? What's the advantages of this Jitsi, Elias? Like, this is the first time that I'm using it.
So same here. I just like that it has this connection to the live streaming on YouTube.
Oh, that's pretty cool.
So I think we can see your screen. Yummy.
That's good. Okay, so hi everyone. I mean, before I get it started, I would like to say, like, I'm really happy to see that many contributions. Contributions have increased dramatically to the NeurIPS community and from our Austrian institutions, and I'm really excited about this because it shows. I mean, we need to have this kind of representation, and it would be really nice if you see anything that you like, and if you want to collaborate, get in touch with each other to increase.
Sorry, I don't think you're sharing. At least I'm not seeing anything.
Am I sharing my screen or not?
Not
I don't know what.
Please try again.
No, I'm not. I wasn't talking about my work yet, but still. You don't see my screen now?
No, it won't. No.
Oh, that's weird. Do you see my screen?
Now, yes.
Okay. Do you see still? All right.
Great.
Cool. So back there in 2016, we had only 2 contributions, and now we have many contributions to NeurIPS, and which is pretty impressive. And all right, so let me get started on sparse flows. So this work was done with my colleagues at MIT. We've been working on looking at continuous time neural networks in terms of how their representation would change if you add sparsity to the network. So when a neural network F is parameterized by the derivatives of its hidden state Z of t, for example, the resulting dynamical system is called a continuous time neural network, okay, or as it calls neural ordinary differential equations. Neural ODEs transform the depths or the time space of a computational graph into a continuous vector field and give rise to a set of functions that was not being able to generate. We weren't being able to generate before. They can be used both for inference and for generative modeling. Okay. So in this work, I'm going to focus mostly on the generative modeling aspect of neural ODEs. Continuous dynamics given by neural ODEs can be significantly helpful in terms of computational efficiency in generative modeling, such as the normalizing flows framework. A normalizing flow computes the log density of a target, a more complex kind of distribution, from a base distribution P of Z0, by the use of the change of variable formula on an invertible mapping. Computing the log determinant of the Jacobians, basically this term here, which in the change of variable formula, is actually very complex for discretized normalizing flows. And if you change that to a continuous time normalizing flow, you can change this computation from log determinant of the Jacobians to a trace operator. Okay. Then there are ways that you can even estimate that trace. It was shown in a paper called Freeform Jacobians Normalizing Flows, which is fewer, that you can really estimate the trace with the constant complexity, with linear complexity actually. So like to graphically illustrate like how normalizing flows work, it's like you have a base distribution, you pass it on to a neural ODE instance, and then you get a more complex representation. Now, if you, under the uniqueness condition, we can say that uniqueness condition of this ODE or this flow, then and its Lipschitzness, then we can say that we can run this ODE backwards. So basically, you have a mapping from a complex distribution to the base distribution and the other way around. This way, you can go from you can get access to the density at every single point in the during the transformation. This is something that you don't actually have access for GANs, for example, or for other variational autoencoder frameworks. It's one of the advantages of these CNFs, that they do not need to optimize. They can directly minimize the log likelihood, negative log likelihood. So to understand, like this is the objective of our paper. So we want to understand CNFs better. In this work, we used pruning as a toolkit to manipulate densities in a series of generative modeling tasks. We first look into some basically these are like going to be like some toy density estimation examples, such as like the spiral. If you have like a density that is looking like a spiral, or you have a Gaussian spiral, like some Gaussian distributions placed on a spiral, or the last one is a Gaussian distribution, we see that if we perform pruning of the underlying neural ODE up to a certain point, like this is now the performance that we get if you just have a fully connected neural ODE system. And this is the kind of representation that they can capture. You see that there are some mode collapse. And by mode collapse, we can see that the kind of connections between there is still like the modes of the different modes of the system has not been disentangled properly from each other. So we see that up to a certain degree of sparsity, for example, here for this one, up to 70% sparsity in the network improves generalization of these models. So how did this happen? Okay. So one of the claims that we have in the paper is that the sparsity helps avoid mode collapse. Okay. So to really get deeper into the roots of this, we looked at the vector field generated by an unpruned vs a pruned kind of network. On the top, you see the unpruned network, the vector field corresponding to the representation they learned. And on the bottom, you see the 70% pruned network. So we see that vector fields in this black region that corresponds to an actual mode does attract all samples inward towards that specific mode. You see that the arrows, the small arrows, are inward. So they are attracting the modes inside. But when you look at the unpruned network, in between modes are also some attractor vectors. Whereas when we look into the pruned network, this attraction is gone. So the vector field actually learned to even send direct the samples outside of those in-between modes. Okay, and this is something empirically interesting to observe from looking into how pruned networks change the vector field representation of a continuous flow. So to go a little bit more, like find a quantitative measure for this, we have like we can compute something that was discovered in 2017. I think the paper was vegan. And so there, what they say, let's draw some sample from a trained normalizing flow. And then the samples are of good quality if they are within 2, 3, or 5 standard deviation from the nearest mode in the system. And then you report the percentage of the good samples of how well the generative model captures mode. That could be like one measure. So then we perform this analysis like on one of the data sets. We see that as we prune, the performance, the kind of the number of quality or the percentage of the good quality samples increases, okay, up to a certain pruning ratio. And then afterwards it decreases. So that's another quantitative measure that indeed that's the case, okay? For example, if you look at a sample from how the distribution of 6 Gaussians were captured by 0% pruning versus 52% pruning, we can see that there is a complete distinction between the two. We saw that even on a larger scale kind of data set, like MNIST data set, like there, because the complexity of the task is higher, let's look into the modes with higher kind of standard deviation. We see that even there, the arguments on mode collapse and capturing the good quality samples exist. So we see that with a little bit of pruning, you would be able to improve the number of good quality samples in normalizing flows. So here, what we see like on these toy data sets, again, just to show you the loss as a function of the pruning ratio, we see that we can really prune networks, and this is consistently it decreases the like up to a certain pruning ratio. In all these examples, we get a better performance. We show the same results here for a set of like tabular data sets. These are real-world data sets, and what you're seeing in the green and in the blue, they're basically unstructured and structured pruning. Unstructured pruning is weight pruning, and a structured pruning is filter pruning, okay, or a group of weights pruning, basically. Then even on the image data sets, we see the small bell curve shape for generative models for image data sets. In all experiments, unstructured pruning leads to a better performance compared to the structured pruning. And that's also very consistent from the pruning community, that weight pruning always performs better, but a structural pruning has its own advantages that we can discuss if you're interested. There is another argument that we say that there's a hypothesis that we have that pruning also avoids sharp local minima. So basically, if you look at this, like why sharp local minimas are bad, because if you have a training loss that has a sharp minima, then its corresponding test loss is high. Whereas if you have a flatter local minima, its corresponding test loss is closer. So look at the test loss here and the test loss here. So we want to avoid sharp minimas in optimization problems generally. So we did an empirical Hessian-based kind of investigation, because if you compute the Hessian of your loss, then you would be able to see the curvature. You know, you can estimate the curvature, and you can see how good you're doing. So we observed that for neural ODEs, pruning decreases the value of the Hessian's eigenvalues. That means they're getting flattened. So this means like the Hessian is going to flatten the loss, which leads to better generalization, which is very much aligned with previous work on generalization properties of the loss around flat and local minima. So you can look at that paper, Keshar et al., 2017. So now, again, for showing a more quantitative analysis, we used pi Hessian and to analyze the Hessian H with respect to the parameters of the a continuous normalizing flow. This enabled us to study the curvature of the loss function as the eigenvalues of the Hessian determines locally the loss gradients change. Okay, so inspired by the Hessian analysis, there is a paper called I think this is the paper. Recited. So it's Erichson et al. This is like the Lipschitz RNN paper. Okay, they also performed there, and they show that they can get better, flatter local minima if you have Lipschitz RNNs. So there, what we do, we compute the maximum eigenvalues of the Hessian. We also compute the trace of a Hessian and a condition number that is corresponding to the ratio of the largest eigenvalue to the minimum eigenvalue. The smaller maximum eigenvalue and trace corresponds to a flatter local minima. And the smaller condition number shows a more robust network. Okay, but for here, the focus that we have is just on the trace and on the maximum eigenvalue. And we see that again, pruning up to a certain ratio decreases the maximum eigenvalue of the Hessian. Thus, we thought that this could be a reason why it helps generalization. Then we also did an extensive comparison with different normalizing flows that are out there. For example, all the sparse flows are done on Fjord because from the computational complexity, Fjord is very efficient. We see that we get better numbers by sparsifying the network on different tasks. Although there are networks that are being able to achieve better results, for example, than us, but look at the parameter counts, for example. So there's always a trade-off between how large is your neural network and how tractable it can become when it matters to actually look into different stages of your density. If you care about performance versus complexity, this would sparse flows definitely help. And we see on image data sets as well, look at the parameter count of the best performing normalizing flows called residual flows on the MNIST and CIFAR10 data sets, and we see that we can get a better performance there as well. And here, like just showing you an overview, the spectrum illustrating of the performance of CNFs versus their parameter count on CIFAR. We see that the pruning helps generalization with 1 to 5 orders of magnitude less parameter counts. As we go smaller in the Fjord, we can get also a good performance by them. So the takeaway from the paper is that pruning definitely improves generalization in neural ODEs and in continuous flows. For some classification example, you can actually refer to the paper. We also show that there are better decision boundaries constructed by pruned networks and what kind of properties they might have. And then pruning also helps avoid mode collapse in continuous flows. Pruning flattens the loss surface of continuous normalizing flows. And maybe for continuous flows, pruning is all you need. Yeah, and that's it. So the code is also available here under Lucas's GitHub handle. Thank you.
Well, thank you very much, Rahim. That was really interesting, especially nowadays when DeepMind, for example, announced another huge language model with I don't know how many billions of parameters. And then you come and say, actually, pruning is giving you even more generalizations than that. Very, very interesting. I don't see any questions in the chat. So again, a reminder, please post your questions in the chat so we can directly ask. And if there are no questions from the team here, then...
Hello. Maybe a small question. Very nice talk, I would say. an interesting topic. And you did a lot of experiments with also comparing flat minima and so on. Okay, my question is, and you started with some toy examples, yeah, Gaussian, spiral, and so on. And my question is, from a more mathematical point of view, okay, so you by experiments, yeah, you see that there are some improvements in terms of flatness and so on. Yeah, are there also some mathematical insights? Yeah, some mathematical arguments to observe such this phenomenon. So
yeah, so that's a very good question. So the short answer is no. but the longer, more elaborated answer is that, like,
it is for some toy example, yeah. Also
yeah, absolutely.
For minimal setting, I think it should be possible to also tackle this in a mathematical sense.
You could do that, yeah. In principle, you can do that, but the question is this: if you derive something from a toy example, would it scale?
Yeah.
To the larger scale, and can you study it then? You see, so then it's becoming hard. I mean, you might be able to say that, because now that we have like a really good quantitative results and experimental results on this, you might be able to say that yes, like there might be some of the mathematical properties of if you can really drive something on what kind of changes are you doing on the, like, we can compute the Hessians of this negative log likelihood, like analytically, right?
Just like in terms of insights. Yeah.
Yes, that's a good point. I mean, yeah, that would be something interesting to investigate, but we haven't done that. No.
Yeah. Okay. Thank you.
Just want to add something here, Ramin, so we can just, in response to what he asked, we can consider lasso as a special case of proving.
Oh yeah, absolutely.
And we know that L1 is also helping generalization, so we can continue on this.
Thank you very much, Ramin.
Yeah, definitely.
And Rahim, yeah, I guess you can also start already with your presentation. Rahim is actually the only one that is joining us with an accepted paper to ICLR. I hope that the next event that we can organize will be about all the Austrian contribution to ICLR. So, Ramin?
Do you see my screen? Do you see my screen and do you hear me?
I think
perfect.
We were seeing your screen before. I don't see it now.
I didn't touch it.
Okay.
That's why we are testing Jitsi here. So let me just reshare again.
Yeah, please.
Do you see it now?
Yes.
Okay.
Perfect. Please go ahead.
For some reason, if I just start sharing my camera, then it might be problematic. So I don't test it again. Okay, so hello everyone. My name is Rahim, and I'm very happy to take over from Ramin's, because this work accidentally is very related to generalization and the shape of loss landscape. I'm talking about a recent work. This is a joint work with Hani Sedki, Olga Sau, and Behnam Neyshabur, where Hani and Olga and Behnam are coming from Google Research. So the motivation of our work is making ensembles.
Rahim,
I guess.
Can I interrupt you for a second?
Sure.
So just for an information, Behnam Neyshabur is one of the key guys in deep learning for studying generalization. So he's one of the most senior and the most contributor to defining generalization bounds of deep learning in the world right now, in our world. So just to put it out there.
Thank you, Ryan. So our motivation was to make ensemble. I guess everybody is here just got familiar with ensemble, but just as a first step, in order to make ensembles, we have different models, let's say neural networks, each of which already converged. And we want a super model, which is ensemble, which does the task better than these three models, let's say. And basically, there are two ways to make such ensembling. the first way is to do ensembling in weighted space, and the second is to do in output space. In weighted space, we mean doing some averaging. In output space, we train different neural networks and we get voting. So who says for cat, and then just get simple voting. But in this talk, we are interested in weighted space in the following slides. So as I mentioned, in the weighted space, when we are talking about making ensembles, we mean by averaging. But there are at least two minimum requirements for making ensembles in the weighted space. The first one is that two models or more we have already converged are residing in one Bayesian, which means that you can consider a bowl, a flat Bayesian, as just Ramin illustrated. And the second one is that the models already have functionally diverse convergence, which means that if they are not functionally diverse, which means that this does harm the making ensemble. Why? Because if you have two similar solutions, if you make ensembles, this doesn't add any values to your ensemble. So we need two models which are residing in one Bayesian, so we can average them. Secondly, we want functionally diverse solutions. So related works like stochastic weight averaging first try to solve models to be in the same Bayesian. On the right, you can see stochastic weight averaging, where we start from one initialization, we train the network, and later, close to the convergence, we save the checkpoints. And if we save the checkpoints, let's say here we have 4 checkpoints, we can get the average. And the orange part in this figure shows that they are residing in one Bayesian, means that they are having close loss. And then if we can average, then the average would be closer to the center of the Bayesian, which gives us a better loss, or which helps generalization. So this is to make models in one Bayesian. Another try is by Frank et al., which is well known for lottery ticket hypothesis, which defines linear mode connectivity. So if you start from one initialization, train it for k epochs, and then make 2 copies of your models, and then train each of them with different SGD order, then you will end up having 2 different solutions. And he showed that, he and his colleagues shows that these 2 networks are residing in one Bayesian, which means that if you just connect these 2 networks by a line, you start from one and try to get to the other one by linear interpolation, they will reside in one Bayesian. This is a necessary condition to be in Bayesian. And then the first requirement of making ensemble is met. But how about the second requirement? The problem with the stochastic weight averaging and linear mode connectivity is that they showed that this doesn't give good diverse solutions, like great diverse solutions, if they are residing in one Bayesian but starting from one initialization. One solution to have functional diverse solution actually is to start from 2 randomly initialized networks. So θ1 and θ2 are start from 2 randomly initialized independent solutions, initializations, and let's train them for k epochs until convergence. Then we have θ1t and θ2t. We are happy with their diversity. However, Frankel shows that if you just get the average out of them, like make ensembles simply, this ensembling would fail, meaning that their averaging would end up in a high loss. So we don't have this. We have a solution which is in one Bayesian, but on the other hand, it's not functional diverse, and vice versa. So we had the research question: is there any way to make different solutions in one Bayesian, so to have great advantages of both worlds at the same time, or not? So in order to answer this question, we had a conjecture. So let's assume that we have 4 different networks, each of which already trained, converge to different solutions. Let's call them A, B, C, D. So this is why they are in the dark zone, which means that they already converge in low loss. And then based on Frankel related works, we know that between each 2 solutions, let's say between A and B, there is a barrier, right? If you start from B and try to get to A, you need to go to high loss and then goes down to low loss. But our conjecture says that for each of these pairs of models, there is a permutation that if you can find such a permutation, you can apply to each of these models. And then you apply such a permutation so that B, for example, goes to B prime, which is in the same loss landscape or Bayesian of A. Then you can get the average of A and B prime or all of these 4 models in order to get better ensembles. And in the following slides, I'm going to show why this conjecture holds. So in the first half of the paper, we are trying to show the effect of different hyperparameters on the flatness or on the flatness of the loss landscape. As we know, based on also Ramin's talks, that flatness, the flatter the better, right? The flatness gives us better generalization and so on and so forth on ensembles. So let's first have a look on the effect of overparameterization on the flatness of the loss landscape. Here we see an MLP which has only one hidden layer with different widths. So we start from 4 neurons to 32K neurons. Let's for a moment focus on MNIS, which is the blue line here. So let's assume we have 4 neurons. We have 2 networks, each of which has 4 neurons. We already trained them, already converged, which means that the loss is close to 0. And if you start from 1, in order to get to the other one, you will face a wall which height is around 40%, right? This means that the first one on the left. And these plots, we found through this experiment, we found that if you increase the number of parameters, this ultimately goes to an overparameterized regime, which everything is flat. So if you have 2 networks, let's say each of which has 1,000 neurons to the power of 10, then there wouldn't be any barrier, which means that everywhere, if you look, is flat, and then you're happy with the generalization and making ensembles. The other observation here is that for all of the data sets for MLPKs, the barrier size in the loss barrier size means the amount of dampness that you have it in your loss landscape. It first goes up and then goes down. That reminds of deep double descents, which almost everybody probably is here familiar with deep double descents with the loss landscape. So here we also have the double descent effect, but in the barrier instead of the loss. So we did also the same experiment with other architectures. Here we have a shallow CNNs, which we have 2 layers. Instead of MLP with 1 hidden layer, we have CNNs, but with 2 CNNs. And same happens here. So we first go up and down, which means that overparameterization removes the barrier. We also did it for VGG and ResNet. However, for deeper networks like VGG and ResNet, we see that the barrier saturates at high level. So I can informally say that the loss landscape for deeper networks is very bumpy. And then we don't go up and down. It's always high level. Okay. This concludes to the effect of depths. So far, we see the effect of width or overparameterization. Here we have the effect of depths. Let's focus for MNIS, for example, here again. So if you have MLP with 1 layer, 2 layer, 4, and 8 layer, the higher the depth is, the higher the barrier would be. So if I'm an engineer, that would be better to have 1 hidden layer MLP instead increasing the width to get better generalization other than increasing the depths. We also had the same phenomena for also VGG and ResNet. So far, so good. We just observed what's the effect of overparameterization and depth over the loss landscape because we are looking for flatness. However, in the second half of the paper, we just want to prove the conjecture. Just as a recall, the conjecture says that for each of these solutions, we are going to find permutations. So that if we apply permutations, then everything would be smooth and they are in the one basin so that we can average them. Before going to show or prove the conjecture, let's define 2 scenarios. The first scenario is real world. Real world is the scenario that we got used to it. So let's assume that we have 4 different solutions, 4 different initialization, which are black dots here. And then we just train them as we got used to, okay? And then after a couple of epochs, we converge to red dots. This is what we call real world. That's it. However, in our model, we have 1 initialization. We just train 1 network, let's say MLP or CNN. And then after convergence, we apply random permutations to each of these to such a solution. And what do I mean by permutation? Let's assume a simple MLP with only 4 neurons. With 4 neurons, we have 24 permutations, right? So you can change the order of these neurons. And hence you can change the columns of incoming and outgoing bits. This is what we call permutation of hidden layer, or permutations of neurons of MLP or channels of a CNN. So here we have started from one initialization. We apply, let's say, change neuron 1 and neuron 2 in 4 neurons, neuron 1 and 4, so that we have now 3 different combinations of neural networks. Okay, this is what we call the R model. And R model has a nice property. R model is already satisfies the conjecture. Recalling the conjecture for our model, for each of these 4 red dots on our model, we know that there exists such a permutation, right? Because we just applied such a permutation. So we can permute inverse such a permutation, and we are good to go. Then we have 4 solutions which are residing in one basin. So we know that our model already satisfies the conjecture. And in the following slides, we are going to show that our model and real world are consistent or similar to each other, and hence we are going to conclude that our conjecture holds. How? By doing a lot of experiments over different architectures and also data sets. We showed that here dashed lines corresponds to real world, and solid lines correspond to our model. Let's assume again on MLP, the bottom up, the top left. Let's assume on the blue one, MLP, when we have, let's say, 1,000 neurons, again, we have 2 networks already trained independently. We just measure what is the barrier in real world, and we also measure what's the barrier in our model using one network. And we see that the barrier is close or very, very similar to each other. Then we can conclude that our model and real world are similar to each other. And we already know that our model satisfied the conjecture. So real world also satisfied the conjecture. So we are not only showing this in our paper, but also we use simulated annealing to actually find such a permutations, because this is what we promise. There exists such a permutation. So let's find these permutations. So we did our best to find such permutations. However, in most cases, we couldn't find it using simulated annealing. But interesting observation here is that if you use simulated annealing, some of these barriers could reduce a lot. Like if you recall from this slide, look at the blue line here, MLP, MNIST. This is not equal to 0 everywhere. But if you use simulated annealing, we could actually find such permutations. So we say that for this network, apply these kind of permutations out of combinatorial search space. And if you apply such a permutation, everything would be flat there. So we not only showed that before permutation, our model and real world are similar to each other in terms of barrier, but also after permutation, this is also true. And this is a summary out of all these experiments, or 4,000 different networks for different architectures, widths, depths, and data sets. And basically, we showed that barrier for real world and our model is close, yet maybe similar to each other, same as real world and our model. And hence, we are going to conclude that our conjecture holds. So the takeaway from this talk is that we know that one way to make ensembles is to weight averaging, and our conjecture says that there might be some permutation. So our way of understanding the loss landscape, the flatness, the sharpness, and this bumpiness might be a hallucination. So if you apply these permutations, there might be no kind of barriers in the loss landscape. So what's better than this? So we can make ensembles, make generalizations, bounds out of flatness. So our theoretical results and extensive experiments also could or couldn't show that the bold conjecture is not true. Thank you, everyone. If there is any questions, I would be happy to take.
Thank you very much. Thank you very much, Rahim. I don't see any questions in the chat. Any questions from us?
Hello, can you hear me?
Yes, yes.
Okay. Well, first, thanks for the nice talk. I would have a question regarding your slide 22, maybe.
22, yes, sure.
I mean, I don't see it anymore, but well, the experiments with the NLP.
Yeah, that's just lets me to reshare it again.
Mm-hmm.
Do you see it now?
Yes, exactly. Thank you.
Mm-hmm.
So my question would be, you ablated the width and the depth, but how do these interact with each other? Like, did you keep the depth constant for the width ablation and the same for the depth ablation?
Okay. Yes, we did exactly the same.
Okay. So like the parameters are not constant, so you add capacity, so to say, in this ablation study.
So for depths, for each of these, if I'm not wrong, so we have only, when we are talking about depths of equal to 1, we have only one hidden layer, which has 1,000 neurons. When we are talking about 2, we have 2 layers, each of which has 1,000 neurons.
Okay. Thank you.
Sure. Thank you.
Okay, so I ask my question, if you don't mind. I wanted to know how the barrier in the y-axis is calculated. Is it with the increase of loss after averaging the parameters of 2 different initializations, or how is it measured?
Yes, actually, this is measured based on loss, but for our plots, in order to compare them like fairly, so in order to better compare, to have better comparison, we are showing accuracy. So when we have loss over like 40%, means that model 1 has already gained 100% accuracy, the other one also have 100%, but if you connect them, then you would have a loss, then the average would have an accuracy of 60%.
Right.
So
for a given width, you would train 2 different models and then would average the weight. Is that right?
Yes. In order to get the yes. And
Just
this average is the ensemble.
Right. There is a delay. Sorry. So
does this
2
answer
different
your
initializations, right?
Yes,
okay,
exactly. This is the real world, right? 2 different initialization. We train them. We get the average because we are caring about ensembles, and we look about what is the barrier over these ensembles. So we start from 1, and then we see that's what's the height of this wall between these 2 solutions at the average.
Got it. Thanks.
Thank you.
I would have a follow-up question, the previous question regarding the layer depth. First of all, also great work. Thanks for sharing with us. Did you consider any measures by going deeper about balancing out the gradient, sort of the lack of gradient flow?
No, not actually.
Since you encountered always increasing loss and barriers, so to say.
No, so you're asking about the reasons why depth is hurting the loss?
Yes, exactly. This goes in that direction.
No, actually, that would be a nice direction to follow up.
Okay. Thank you.
Thank you. So if there is no question, Leah, the floor is yours. Thank you.
Thank you very much. I think, I don't see any more questions. I find it very interesting, this your work. In the past, there was a talk from in 2016. There was a talk from I forgot the name, after D something, and he said that the network should be more deep, and then you come and say it should be more thick, not more wide. That's very interesting. His paper was, by the way, disproved, so I would take your approach. So our next speaker is Elias.
Yes, hi. Can you hear me? And can you see my screen?
I believe so, yes.
Yes.
There we go. Okay, so hello everyone. I will be presenting our work with the title Efficient Matrix-Free Approximations of Second-Order Information. And this was joint work with Eldar Kurtic and Dan Alistair, and we're all 3 from IST Austria. Now, to start with the motivation of our work, So second order information, actually, as we've seen before today in Ramin's talk, where he also used the Hessian matrix to study some generalization properties. But this Hessian matrix and also its inverse have quite a few applications, for example, for optimization or pruning, or the generalization we have seen before. But the problem is that for modern neural networks that have like millions of parameters, it's basically impossible to compute this matrix exactly. In fact, it's actually even hard to just approximate it, because this matrix is a d by d matrix, and d, the number of parameters, is 1,000,000. So this is extremely expensive to store in memory. And if we need the inverse, it gets even worse, because then we have to invert this d by d matrix, which takes d cubed time. So you need quite a few tricks to work around this. So some common approaches are, for example, that you don't approximate the full matrix, but just the diagonal, or just small blocks along the diagonal. But of course, you lose quite a lot of information by doing so. And now, a more specialized approach that only works for certain approximations of the Hessian is that you use the fact that sometimes you don't need the matrix itself, but sometimes you, for example, only need to multiply the inverse Hessian with some vector. And for certain approximations, you can actually write this matrix vector product in a way that you can completely avoid like any intermediate d by d matrices. And in fact, we take a similar approach in this paper, where we introduce new such matrix-free methods that work for certain kinds of Hessian approximations, in particular ones that can be written as the sum of rank 1 matrices. And one very well-known and also useful such approximation is a so-called empirical Fisher approximation that's known to be useful in pruning neural networks and also in optimizing them. And this approximation works as follows. So you basically sample m, a small number of gradients from your network, and then you compute the average outer product matrix plus some dampening to make it invertible. And this is called the empirical Fisher matrix, and that's the proxy for your Hessian. And one nice property about this approximation is that because you only have a few gradients m, this is a low rank matrix. And so you can actually use a low rank matrix inversion formula, the Woodbury recursion, to reduce the inversion time from d cubed to d squared m, which, since m is usually quite small, is a massive improvement in terms of computation. But there is still one big problem. Like, if you naively want to execute this recursion, you still need d squared memory, which, as I discussed, is far too much for bigger neural networks. Now, a recent work called Wood-Fisher made this tractable by doing a blockwise approximation and managed to get pretty good results with that. But this method still has quite a few shortcomings. Now, the computation time and the memory depends on the dimension as well as on the block size. And if the block size gets closer to the ideal case, so close to the full matrix, then we still have this d squared memory, which is intractable. So this method can only really be used for small blocks. And the second problem is that if you want to replace some of the gradients in your approximation, because this formula is recursive, you always have to fully recompute your matrix. So this method cannot really be used in situations where it's important to have a dynamic approximation. For example, like you would need in an optimization setting. And what we do in this work is we introduce two new algorithms we call M-FAC, which address exactly these problems, and additionally also give pretty big speed ups in practical implementations. Now, first, we introduce the static algorithm, which targets like a pruning setting where we have one static Hessian, and we need to extract individual elements to compute pruning metrics. And our method supports this in time and space that is d times m. So it's linear in the model dimension and also linear in the number of gradients. And it's independent of any block size, so it can actually be used for the full approximation. Now, second, we introduced the dynamic algorithm, which, for example, useful in optimization, where with a small, like extra m cubed or m cubed computation or m squared memory factor, we can actually dynamically change gradients in our approximation, which will be important for optimization, as you will see later. Now, so roughly how does this work? I will only cover this very briefly. But for the static algorithm, kind of the main idea is that you unroll this Woodbury recursion, and then you perform the computations in a very specific order. so that you can actually avoid, and also you reuse some pre-computed recursive values. And you do this in a way so that you can actually avoid any matrix vector multiplications that would require intermediate D by D matrices. And this way you can compute the inverse Hessian vector product approximation in time linear in D instead of in D squared. Now, for the dynamic algorithm works a little differently. Here we use, here the main insight we use, which we prove in the paper, is that when we're dealing with such a sum of rank 1 approximation, and we want to multiply this with a vector x, then actually we can write this as a linear combination of the gradients in our approximation, as well as the vector we're multiplying with. And most importantly, actually, these coefficients can be computed with also by maintaining some intermediate matrices efficiently. It can be computed efficiently, in particular efficiently when we want to change gradients, we can update those. And this way we can this way we can design a dynamic version of this inverse Hessian vector approximation. And yes, so that's kind of the general methods. And now let's look into some of the results of how they actually perform in practice. First, we look at the pruning scenario where we want to delete some weights from networks, as many as possible, and lose as little as possible in terms of accuracy. And here we basically slot in M-FAC in the optimal brain surgeon framework as the Hessian approximator. And so if we run this in exactly the same setup as a previous work, like Wood-Fisher, we can already see that because our method is fast and allows bigger parameter settings, we can get slight improvements. But actually, our method is so much faster that we can kind of redesign the pruning schedules and do, for example, many more Hessian calculations without increasing the total time. And by doing this, we can actually improve the results over Wood-Fisher, which was the previous state-of-the-art method, by quite substantially, especially for higher sparsities, as you can see here. Now, for the second application, we look at optimization. And here we use the dynamic algorithm that I explained before. And here we basically use the dynamic algorithm as a Hessian preconditioner for the gradient in vanilla SGD. So somewhat like Newton's method, just with an approximation of the Hessian. And most importantly, we don't use momentum, which is usually very important for first order methods and also other second order methods. And here in the first test on some wide ResNet and the CIFAR 100 data set, we can already see that the M-FAC method optimizes the loss fastest in this short training schedule, which is exactly what you would expect from an optimizer that uses rich second order information. And what I think is particularly remarkable here is that we can see that the gap between SGD without momentum and M-FAC, which also does not use momentum, is pretty big. So this actually suggests that our approximation must be pretty good to make up for the lack of momentum, which actually seems to be not needed for our method. Now, in a bit more realistic scenarios where we consider some bigger networks and also some ImageNet data sets, and we run in standard, like with standard parameters or standard learning setup, and compare with SGD and ADAM, we can see that M-FAC, the M-FAC optimizer, performs on par actually with SGD, usually considerably better than ADAM, and sometimes even slightly better. And because our approximation is pretty efficient, we can also see that the overheads are only quite moderate, which are usually for other second order methods. These are the overheads are very big, but these are like about 20 to 40% is still somewhat reasonable. And in particular, also if you look at optimizing sparse networks, where actually our method scales very well with sparse networks. So the overhead drops significantly actually, and is actually on par with, say, SGD. And we seem to pretty consistently get better results. Now, and finally, we also look at some natural language processing tasks. Here we look at the small versions, like some of the smallest BERT models, which is a very common transformer model used in natural language processing, and compare it with kind of state-of-the-art ADAM numbers, and state-of-the-art atom numbers on various GLUE benchmark tasks, which is like a suite of various natural language processing tasks. And we can see that M-FAC seems to pretty consistently outperform the atom baselines on almost all the tasks on these small transformer models. So to summarize, in this work, we introduce new efficient matrix-free methods that allow us to deal with the inverse of a Hessian approximation that can be written as the sum of rank 1 matrices, like for example the Fisher matrix. Now, and our method makes it tractable to actually work with the full matrix, not just the blockwise approximation, and it allows fast replacement of gradients, which means that it can also be used in dynamic settings. Then we actually showed that our method produces state-of-the-art results in pruning, and we also showed some good early results for optimizing smaller transformer models. And the code can be found on GitHub. So thank you for your attention, and I'm looking forward to answering your questions.
Thank you very much, Elias. Yeah, the matrices of the transformers are always the bottleneck in terms of memory. So it's good to see that.
Yes, I mean, even though our method makes this Hessian stuff a lot more efficient than previous methods, still we can only unfortunately run it on the very smallest transformer variants.
Yeah.
But yes, but so perhaps in the future we will look into seeing if we can actually scale this up a bit more to bigger transformers.
Yeah, and I'm very looking forward to see what the next, how the future work from you guys would look like. Do we have any additional questions from here, from the chat?
Hi, Elias. This was very nice, and I'm pretty sure I'm going to use your optimization method at some point. And so I was wondering, what kind of limitations do you have? What are the limitations right now? Technical limitations.
So I mean, the main limitation of this method is that you need to store kind of M gradients. And M actually still needs to be reasonably large. Like, for example, for most of our experience, we use M equals 1,000. And obviously, for models that have more than, say, 10 million parameters, this starts to get pretty expensive to store. So I would say this is kind of the main limitation currently. I mean, there are some hopes, for example, in improving this by introducing some kind of blockwise stuff again. But with very big blocks, which might allow you to reduce the number of gradients you need. Because the reason we found we need this relatively big number of gradients is because it seems that if you have fewer gradients like this, the approximation simply is too noisy. And but you could perhaps circumvent this a bit by introducing the somewhat blockwise, for example, a block for a few layers. For a few layers together again. Or you could try to look into compressing the gradients you store in some way, I don't know, with lower precision or actually with sparsity. But yes, so
interesting.
That's the main limitation currently is the memory cost. But although it should be noted that the memory cost is most problematic for optimization, because there you need to be really fast. Whereas for the static algorithm for pruning, this is less of a problem. Actually, we have an implementation which kind of swaps memory between CPU and GPU memory quite efficiently, and this way you can actually scale to pretty big models for the pruning part, because you're not because the speed is not that critical there. But for optimization, you need to keep everything in memory. Otherwise, you're just not fast enough.
That was my next question. You just answered it as well. Awesome. Great work.
Thank you.
Thank you.
Thank you very much, Elias. Really, really great work. So our next speaker is Alexandra, going to talk about AC/DC, electricity of deep learning.
Hello, thank you. Thank you for inviting me. I will try to share my screen. I hope you can see it.
Yes.
Okay, then I will Okay, let's hope it works with the camera on then. So thanks again for inviting me. I will be talking about ACDC, which stands for Alternating Compressed Decompressed Training of Deep Neural Networks. And this is joint work with my colleague Jen, Adrian Vladu, and my supervisor Dan Alistar. Of course, we all are very well aware that neural networks are very big and very successful, but this, of course, comes with the significant time, space, and energy resources required for training. And unfortunately, such requirements do not favor the deployment of deep learning models to edge devices such as mobile phones. And one of the solutions that has emerged in recent years to this problem is to prune the models, which means, as you've seen also from Elias' talk, to remove by setting to 0 as many neural network parameters as possible, such that the model accuracy is a little impacted by this. So in a nutshell, neural network pruning creates sparse models, which would need less storage space and lead to reduced inference times. And one of the most popular choices is to simply set the weights with the smallest absolute value or magnitude to 0. And the pruning literature has been very vast, and many of these methods for now fit into the post-training pruning category, which means to start basically from a dense pre-trained network and to then gradually proceed to prune the network and fine-tune it until a certain desired sparsity level is achieved. Unfortunately, using this kind of pruning method, you can only obtain benefit from inference time speedup. And of course, these methods require longer time to train, as you also need access to the dense pre-trained model. And one question that has gained a lot of interest recently is how can we train sparse models from scratch, such that we don't need access to the dense pre-trained model anymore. And this has given rise to the sparse training paradigm, where both the weights and gradients are sparse for as long as possible during training. And this would lead to potential training time speedup, which of course for now is only theoretical. And because there is no specialized hardware for that, but there is work on it. For example, GraphQuare IPUs is such a hardware implementation. And also in terms of the literature of sparse training, it has also seen a rapid growth. For example, Topcast and Wriggle are two examples of papers from last year at NeurIPS and ICML, which have shown that models obtained through these methods can be very competitive, both in terms of inference flops and prediction accuracy, to those obtained through post-training pruning methods, with the additional benefit of training time speedup. And with these motivations in mind, we introduce our method, ACDC, which is in fact a hybrid pruning method, alternating between dense and sparse training phases. And in practice, it acts as a regularizer, and we can also, with this method, co-train sparse and dense models. And our method is inspired by, theoretically, by the iterative hard thresholding literature. And there have been similar algorithms proposed in previous years, such as skinny deep neural networks or dense sparse dense. But we are the first one to show that you can obtain highly accurate sparse models on modern architectures with this method, especially for high levels of sparsity. And in addition, we show theoretical guarantees for our method, and we show several other properties, such as the fact that you can co-train sparse and dense models. We studied the behavior of these models on memorization, and also they can lead the weight to better interpretability. So in terms of theoretical guarantees, I'll first just briefly sketch the iterative hard thresholding background. So basically, IHT aims to optimize a function with sparsity constraints on the parameters. And it starts at any given time iteration for any parameters theta t. You proceed by applying a gradient descent step to which you apply the top k operator, which selects the k highest values of the parameters in absolute value, and then sets the rest to 0. And this algorithm has been is known to have good convergence guarantees for convex models. But of course, to translate this to deep learning training, we require a few changes, since of course having the gradient descent step is not feasible for large models and large data sets. So instead of using a single gradient descent step, we replace it with a multiple dense SGD updates, which will form the decompressed phase, the so-called decompressed phase. And after this phase, we compute the masks based on the magnitude of the parameters. And with this fixed mask, we optimize in the sparse support. And this will form for a few epochs, and this will form the compressed phase. And then we reintroduce the pruned weights with the value 0, and we reiterate through this procedure multiple times until we reach the end of our training cycle. And in terms of the theoretical guarantees that we prove convergence for a variant of IHT, which we call stochastic IHT. So basically, instead of using the gradient descent step, we use an unbiased estimator of the gradient. And more notably, we show convergence beyond convex functions, so a bit more complicated setup. And also through our theoretical analysis, it becomes apparent that, in fact, dense SGD steps are necessary for convergence. So they do lead to better sparse models and better masks implicitly. And also the sparse SGD steps are beneficial as long as they decrease the loss function, because they offer, of course, the potential for training time speedup. And also our results, theoretical results, shows that if the model allows for more sparsity, then this would imply faster convergence. And we also show that by modifying this proof, we can show convergence of the algorithm we use in practice, so for ACDC. So namely, if we use multiple consecutive dense SGD steps, such as in our dense training phase, stochastic IHT still converges. And optimizing in the sparse support is beneficial, as I said previously. So together, these two would suggest that, would actually confirm that ACDC has theoretical guarantees to support its good experimental results. So in terms of results, here I show results for uniform sparsity for ImageNet trained on the large-scale ResNet 50 model. So uniform sparsity means that each layer of the network is pruned to the same sparsity levels. Here is like 90% and 95%. And we compare ACDC with Topcast and Wriggle, so the top performing sparse training methods, with increased training time. So if we increase the Topcast training iterations by a factor of 2 or 5, and similarly for Wriggle. And we plot the validation accuracy versus the number of training flops as a fraction of the dense flops. So these plots show that ACDC with uniform sparsity has similar or better performance than Topcast run with 2 times the number of iterations at 90% sparsity. And ACDC is also similar to Wriggle 5x at 95% sparsity with similar training costs. But if we increase the number of training iterations for ACDC 2 times, then we surpass both Wriggle and Topcast at 2 and 5 times the number of iterations. And next, I will show that we actually obtain better results at high sparsity, so 95 and 98% than previous methods, at least during the time the paper was submitted. So for global sparsity on the same ResNet 50 architecture, you can see in this table that ACDC at 80 and 90% sparsity, so medium level sparsity, is very close to post-training pruning methods, which are considered to be state-of-the-art in this category. But for high levels of sparsity, so for 95 and 98% sparsity, we surpass the existing methods in terms of accuracy. And also we show results on other architectures. So on MobileNet v1, similarly trained on ImageNet, we obtain better accuracy than existing methods. And also we show some experiments on transformer models where we are better than the competing Topcast at 90% sparsity. And for some additional properties, as I briefly mentioned before, we can co-train sparse and dense models. In fact, the dense models trained with ACDC can recover the dense baseline accuracy after a short amount of fine-tuning. So in this table, I show the results for ACDC trained on ResNet 50, and the dense models after a bit of fine-tuning, which were initially trained with like 80 and 90% target sparsity. So you can see that they almost recovered, at least for 80 and 90% sparsity, the baseline accuracy. And additionally, in terms of sample agreements, so how many samples do the ACDC sparse and dense models agree on? In fact, this number is higher than for the corresponding models obtained through post-training pruning methods. So between the post-training sparse method, a sparse model and its corresponding dense baseline. So this would suggest that having this co-training method can open the path to better interpretability between sparse and dense models. And also, in terms of memorization, we show that the sparse models obtained with ACDC are less likely to memorize random labels. So in this experiment, we have a ResNet 20 model trained on CFAR10, to which we inject noise in the labels of a small subset of the samples, training samples, and we track their accuracy during training. So in fact, at high sparsity, so here 95% sparsity, the ACDC model still correctly classifies the perturbed samples with respect to their true labels. So not only does it not memorize the perturbed label, but it still learns to classify correctly the samples. To conclude, I discussed about method for co-training sparse and dense models, which starts with a short warm-up phase, and then it proceeds to alternate between sparse and dense training. And it ends with a fine-tuning phase, which can be either sparse fine-tuning to obtain accurate sparse models, or dense fine-tuning to obtain dense models that can recover the dense baseline accuracy. Thank you, and looking forward for questions.
Wow, that was very interesting. Thank you very much, Alexandra.
Thank you too.
I don't see any questions on the chat. Does any of the guys here online have questions? Oh, can you hear me?
I hear you, yes.
Okay. So I see only that you were training a lot, like 100 epochs and such. And I think that also Mathias has a question.
Thanks. Yeah, nice talk, Alexandra.
Thank you.
In terms of training epochs, how was it, like 100 epochs on ImageNet, I suppose, right?
Yeah, so so there was minimal hyperparameter tuning. We didn't modify the setup we use for the dense baseline training.
I see. The dense baseline also gets 76 point something.
Yeah, 76.8, I think.
And the transformer XL, was it faster or slower in terms of training?
It's the same. We didn't prolong training or didn't modify the training.
Okay. Yeah, thanks. Yeah.
I had a question. If you could tell me if you had any experience on layer collapse, and if you had any mechanism to prevent that when training your models. because I see you reach very high sparsity, and usually if you're using some magnitude pruning or similar approaches, it's going to be problematic for the layer collapse. Thank you.
So I guess by layer collapse, you mean that the whole layer was pruned, or?
Yes, exactly.
Yeah, so I didn't notice this. I read in a few other papers that this was mentioned as a problem, but I haven't experienced this. And also other papers that do global magnitude haven't experienced this. So for example, in Woodfisher, or I think also Elias's paper, this hasn't been a problem. So
very interesting.
Yeah. What I saw that happens with these models is that, of course, there are like neurons that, or like channels or filters that get pruned if you have a lot of sparsity. And when you reintroduce the weights, since the whole channel was pruned, you no longer receive gradients, so those channels are never activated again. So in a way, our method introduces some kind of structured sparsity, but it's not, it's not a lot of structured sparsity.
It kind of implicitly creates it somehow. Interesting.
And also if we use like low sparsity, so for example 50% sparsity, I said it acts as a regularizer because in this regime we actually improve a bit over the dense baseline. So yeah.
All right. Thanks a lot.
Thank you.
Maybe I can also briefly comment on the collapse issue. I think one thing that also helps here is that this is a ResNet. Like in some experiments we did, we also noticed that, for example, you can easily prune several layers to 99% in the ResNet 50, for example, without having any like significant accuracy drops that you would expect from basically fully pruning a layer. So I would guess that this is perhaps also one of the reasons why this is not so problematic in the experiments that Alex and also I did.
Thanks for sharing the details.
Thank you very much, Alexandra, and thank you.
Thank you too.
It's wonderful to see these results, especially from my point of view, the wiki text, very nice improvement there as well. I don't know if you guys can hear me.
No, I didn't hear if you said something in the last 10 seconds. I didn't hear it.
I maybe have another short question. So that is about the structured sparsity that seems to appear. So I assume that once you prune a filter, that it's never getting trained again, or?
Yeah, that was also my impression on what happened.
So I was wondering if maybe you tried like to, for example, reinitialize this filter so that the dense phase can then start to introduce it again if it's helpful, because it would seem that fully pruning a filter is probably not necessarily the best for sparsity for an unstructured model.
Yeah, I mean, we didn't try that, but it would be interesting indeed. But I think it didn't really hurt. So we also have a follow-up paper on a sparse transfer, where we test like different sparsity methods and how well do they transfer on different downstream tasks. And in fact, it seems that this property of ACDC of pruning channels might be helpful somehow, might induce some regularization effect. So yeah, I mean, maybe it's worth trying to see if reinitializing those channels would lead to better sparse models, but maybe it also has some beneficial effect. So it's hard to quantify which one it is.
I mean, I think it's in general pretty rare for like an unstructured pruning method to start pruning like anything more than 1% of the channels or so. So I think that's actually quite interesting about this method.
Yeah, I think it's something that probably you don't really see with gradual
Yes,
pruning.
yeah, no, you don't see it there. And perhaps do you know if these filters start getting pruned already early or just in the very last few steps?
I think even quite early it happens.
Oh,
It
okay.
starts happening. Yeah.
Okay, interesting. Thank you.
Thank you.
Thank you very much, Alexandra. Okay, our next speaker is Georgi.
Yeah, so let me try to share the screen.
Yeah. Asynchronous. Asynchronous.
Can you see it?
Yes.
Okay, now.
Oh, now yes.
All right. So, yes, I'm Georgi Nadiradze. Thanks for invite. And today I'm going to talk about asynchronous decentralized SGD with local and quantized updates. This is joint work with Mojtaba Sabur, Peter Davis, Shigangli, and my supervisor, Dan Alistair. So to jump into it, we consider the version of classical decentralized learning setting. We assume that we have n nodes on a graph G, and each node I has a local model Xi and some local data distribution Di. Using them, node I can compute stochastic gradient Gi, and it tries to optimize non-convex local loss function Fi using stochastic gradients. So nodes proceed in asynchronous pairwise steps. Each node takes some local gradient steps, then chooses neighbor uniformly at random, and averages quantized models. So the main question we want to answer is, does this converge, and how convergence depend on the graph structure? And we also want to have some results with experiments. And why is this type of algorithm? First, we use local steps to decrease the interactions between the nodes because they are costly. We use asynchrony to avoid synchronization costs, and we use quantization to reduce overhead from communication itself. So now, just briefly, in the literature, it is well known that asynchrony local steps and quantization can be applied, but unfortunately, they can be applied separately or just two of them. So we want to focus on applying them together. So now our algorithm, which is called Swarm SGD, looks like this at node I. Each node I has a register which contains the current local model Xi, which other nodes update using quantization, and the other register Xi hat contains the outdated local model. So basically what is happening is that I performs computation using Xi hat, and during computation, other nodes update Xi. So hence, Xi is current model and Xi hat is outdated local model. So first step for node I is to compute K local stochastic gradients, where K is geometric random variable with mean age. Then once the computation is done, it picks neighbor J uniformly at random and sets Xi hat and Xi to average of quantized current local models of Xi and Xj, and then it applies the computed local stochastic gradient multiplied by the learning rate theta. And for J, it just updates the current local model of J to average of quantized local models. So the crucial part is here is that I doesn't have to block while J is in computation. But unfortunately, if several nodes try to communicate with J, we have to implement Q so that nodes access J, like based on the Q. So now, as usual, if we take some asynchronous algorithm and parallel steps, the way it is analyzed theoretically is that we take the parallel execution and map it to the sequential one. So in the sequential model, the number of sequential steps is the same as number of interactions between the nodes. So for node I, we take T interactions, and XTI is current local model after T interactions, and XTI hat is outdated local model. Then it's step T plus 1, the sequential step, we activate node I. So this corresponds to the point where I would finish the local computation, and now it wants to interact with some other node. All right, so then we assume that it already computed local stochastic gradients. Oh, sorry. This happened once, but can you still hear me?
Yes, we can still hear you. No worry.
Oh, let's try again. So this happened during my thesis defense, and I haven't encountered it since then, but let's try again.
No problem.
Yeah. Yeah, okay. Yeah, so I finished this computing local stochastic gradients, and then basically it picks neighbor j, and they proceed as is the parallel steps. The xt plus 1i and the xt plus 1i hat is updated using quantized local models. Then it applies computed local stochastic gradients, and then correspondingly it updates the local model of node j. So now what are theoretical assumptions? So as mentioned, each node has local function fi, which it tries to optimize. Then stochastic gradients of node I are unbiased, meaning that in expectation, stochastic gradient is equal to gradient of function fi. Then the gradients are L-Lipschitz, which is quite standard. Then plus we have gradient bounds. For example, stochastic gradient second moment is bound by m squared. We have variance bound on stochastic gradient, and plus if f is average of all local loss functions, then we kind of have to say that the local loss functions don't differ, like they don't deviate from each other much. So this is just assumptions on the functions themselves. So now for the graph, we assume that the minimum and maximum degrees are Ramin and Rhomax, and then the second smallest eigenvalue of the Laplacian is lambda 2. So basically this means that if lambda 2 is large, the graph, like mixing happens much faster, and our algorithm like hopefully converges faster. For example, if graph is fully connected, then Ramin and Rhomax are n-1, and lambda 2 is equal to n. So now for theoretical guarantees, what do we have here? So first of all, we track convergence of ut, which is the average of local models at step t. So we assume that our algorithm performs h local gradient steps of average, on average, where h is some constant. We use a learning rate, which is equal to n over square root of t, where t is the total number of sequential interactions. And also our algorithm requires of d log Rhomax squared over Ramin times lambda 2 plus log t bits per step. So this looks confusing, but like for a fully connected graph, this is basically O of d plus log t. So constant pen dimension and plus log t for analysis reasons. Now the convergence itself, like it's quite standard for non-convex optimization. The left term here, like on the left side, means that the gradients are vanishing. As for the right term, like for example, the green terms are kind of similar as if we ran sequential stochastic gradient algorithm, and the red term is overhead from all the relaxations, for example, quantization, like optimizing on a graph, and asynchrony, and so on. And the crucial point is that if number of interactions t is large enough, this term is dominated by other terms. So basically, we kind of match the convergence of sequential stochastic gradient, even though we had to deal with quantization, asynchrony, and so on. And then, like theoretically, what we usually assume is that since now t is total number of sequential interactions, we can assume that, like, for example, n of them happen in parallel, or some linear number of them. So if in convergence t is sequential, then we can replace it with t parallel times n. And basically what it gives is that we have a speed up of square root of n, which is optimal in this case. So I will not go into the details of the proof because of the time, and I will just try to go through some experiments. Also, I want to mention that I didn't work on them, so like this is what I kind of understand from the paper. So we ran our experiments on Peste supercomputer. We tried to train CNNs and transformer Excel models. So we ran asynchronous variant of the algorithm with like from 2 to 5 local steps. So CNNs, you can look them in the paper, but I'm going to try to explain what happens with transformer models. So we measure time versus accuracy result for 10 epochs, and the baseline accuracy here is 26.1 blue score. So the baseline accuracy we measure, the baseline is some large mini-bet stochastic gradient, which is sequential. And then if we run our algorithm for 10 epochs with 16 nodes, we get that we have 50% speed up. Basically, this means that like we are faster, like we perform epochs much faster than baseline. Now, if we go up to 32 nodes, the overhead I mentioned for being decentralized and asynchronous and quantized a bit overtakes. So instead of 10 epochs, we have to run 15 epochs to make the accuracy. But fortunately, as I mentioned, we are fast enough. So even in this case, overall, our algorithm is 70% faster. And also ADPACD, which is kind of the fastest decentralized asynchronous algorithm, we are 30% faster than its time. So in general, some outperforms other decentralized methods in terms of speed and often in terms of accuracy. And our main reason is that we reduce the communication frequency and apply quantization. On large models, probability can be quite competitive even against large batch SED, and you have to check the paper for additional results. Overall, we provide theoretical guarantees for algorithm which combines asynchrony, quantization, and local steps. Our analysis technique, which skipped, is use load balancing since we average local models, and we kind of prove that the local models don't diverge, so they stay close to each other. And finally, we implement our algorithms in PyTorch and TensorFlow and show that it outperforms other decentralized methods. Thank you for your attention. I'm happy to answer the question.
Thank you very much, Georgi. I again don't see any questions in the chat. Maybe someone here. Okay, thank you very much, Georgi. That was very interesting.
Thank you.
I think it was really impressive to see how you can reach the same results with so much more improvement in the time of training. Not that we have 15 GPUs, but still. Our next speaker is Werner.
Okay, the app is a little bit.
Yeah.
Okay. Can you? I need to allow. Can you see my screen?
Not yet.
Yes, I can see the presentation.
Okay, and now I share my camera. And can you still see my screen?
No.
Okay, I need to share again. Okay, for some certain reason, I cannot share my screen and the camera at the same time. Can you now see my screen?
Yes, and I think also you.
Okay, very well, thank you. So thank you, Liat. I don't know anybody of you. I'm happy that you invited me. Thank you very much. It's a little bit unfortunate that this is not a face-to-face meeting at NeurIPS, right? Otherwise, I could buy you some beer. And I cannot see any of your faces, but I imagine you have now this beer I bought for you, and I imagine you are drinking this beer now.
Actually, we lost both the video and your presentation at the moment.
Okay, so I tried to share my screen again.
But I still have the beer.
That's very nice. So enjoy your beer. While trying to understand this app, So the story of our paper starts some years ago, where I was sitting at the ICLEAR conference dinner table, and there was this one guy who asked the question. So we were talking about unsupervised domain adaptation, and he asked if we are using model selection methods that work under stronger restrictions than the domain adaptations we are tuning with these methods. What do I mean with this? Till our paper now, all the methods were assuming that a density ratio between source and target densities is bounded. All the methods which have theoretical guarantees. And I will present to you now a method which has theoretical guarantees even for distributions with disjoint supports, meaning that density ratio can be unbounded. Can somebody of you give me a small signal if you still can hear me and the app works?
Yes, we see everything and we hear.
Okay, very well. I'm Werner Zellinger. This is a joint work together with Natalia. She's a PhD student at SCCH, together with Marius, who is working at Institute of Machine Learning and Dynatrace Research. Hamid, he's also here, is working at Johannes Kepler University of Linz and the Institute of Computational Perception. Juan, who is working at Research Institute for Computational and Applied Mathematics of the Austrian Academy of Sciences. Bernhard Nessles at the Institute of Machine Learning, also JKU. Also Professor Sergei Pereversiev is from RICAM, and Bernhard Moser is also here. He is the research director from the Software Competence Center Hagenberg. So this is our team. I will invest the next method to tell you something about the problem setting of unsupervised domain adaptation. I will precisely state the problem of parameter choice. Then I will give you some background on the balancing principle, or also sometimes called Levsky's method, for inverse problems. The methods borrowed in this work are from regularized inverse problems. And I will show you our approach, which is to extend the balancing principle for regularized inverse problems to the setting of unsupervised domain adaptation. So in unsupervised domain adaptation, we have given two data sets, a source data set and a target data set, where the source data set is labeled and the target data set is unlabeled. For example, I want to train a model on my webcam image images to separate objects, so to classify objects, but I do not want to label my images. Instead, I want to use a labeled data set from the internet with nice white background to train my model, such that the model has a high accuracy on the target data set. The problem is, of course, domain shift, because the source data set can have a different distribution than the target data set. You can also find a lot of other examples in the literature. Maybe I keep it short, and if you are interested, we can talk about at the end. There is one approach, which is called distance regularization, or invariant feature learning, sometimes representation learning approach. Different papers give different names, which work like that. So you map the input data from the two data sets by a function into a new representation space, for example, activations of neural network by some function phi, and subsequently, or at the same time, you train a classifier on top of this representation to separate the classes. And during training, you minimize a distance between the source and target representation distributions. In this way, you hope that the classifier from the source dataset is adapted to the target dataset. And this is often realized by penalizing the minimization of the source error of the function by some parameter times a distance between the distributions. The problem of this work is to choose this parameter alpha, which is a very crucial parameter because it controls somehow the trade-off between classification and adaptation or distance minimization. So that's the problem of this work. So why do we think this problem is worth solving? So first of all, as I said at the beginning, there is no approach for tuning this parameter which has theoretical guarantees for unbounded density ratio. There are works which have theoretical guarantees for bounded density ratio. This comes from the sample selection bias community, where also Heckman got the Nobel Prize for Economics in the year 2000. But for unbounded density ratio, there is no guarantee. And this is very interesting because this future representation learning approach we are talking about actually has the power to overcome the assumption that the density ratio is bounded. So these methods work better in such settings. But we don't have a model selection method yet for this problem with theoretical guarantees. The second reason why we think this problem is worth attacking is that this parameter has a huge influence on the performance of the domain adaptation methods. And last, it's a little bit unfair if we all tune our domain adaptation methods with different model selection methods and then call these benchmarks. So there is a need for doing research in this direction of how we choose our parameters. Now let me give you some background about parameter choice in regularized inverse problems. Here you can see an optimization function where we compute the minimum of a regularized functional with some error plus parameter alpha times the norm of some function. And if this is Tikhonov regularization, we have error bounds for this kind of methods. So for example, the model F is away from the optimum in terms of norm, can be bounded by two terms, S of alpha and A of alpha. S of alpha often called the sample error and A of alpha often called the approximation error. This is also related to the bias variance trade-off. And if we increase alpha, since alpha penalizes the model and controls the kind of smoothness of this model, we can better sample and sample. The sample error decreases and the approximation error increases. In regularized inverse problems, they also can prove that the balancing value alpha star, which balances the two curves, has some optimality properties. So it has an optimal error rate if you use the model of the balancing value. Unfortunately, the approximation error can never be computed. We can just compute the sample error. And this is exactly where the balancing principle arrives. So the balancing principle is a procedure which allows you to estimate this balancing value without having access to the approximation error. And it is based on the following lemma. So in the box, you can see a lemma. So for two parameters, beta and gamma, which are smaller or equal to the balancing value alpha star, you can prove the following inequality, that the corresponding models, which are minimizers of the optimization functional I showed you before, the norm difference can be bounded by 4 times the sample error. And the interesting thing on this inequality is that it does not contain the approximation error. So you can compute every value in this inequality. And this gives you a procedure for estimating the balancing value alpha star. You can check this inequality for a lot of pairs. And once this is violated, you know that beta and gamma are not anymore smaller than alpha star. So what we do in a sequence of values, of alpha values, we make some kind of sliding window in the sliding window approach, and we move over this sequence and check always this inequality. Once it's violated, we are near the value alpha star. This is the balancing principle according to Lepsky from penalized regularized inverse problems. And now, just very shortly, our approach, which is to extend the balancing principle to domain adaptation. In unsupervised domain adaptation, and this is our main observation, we have a very, very similar setting. So if I may go to the approach before, you can see we also penalize the source error by some, let's call it regularization term, the distance. And you can see on the lower right, you can see an experiment where we implemented it with maximum mean discrepancy regularization of transformed moons. So on a very simple toy data set, you can see that exactly this is happening. Yeah, that the distance is decreasing, and the E, what we call E, a kind of a sum of terms, is increasing. So let me start from a very simple example bound of Ben David. This is a seminal work. You can bound the target error of the model by the source error plus a term that contains label information from the target, which we cannot estimate, plus a distance between source and target representations. And we call the first terms E of alpha and the distance D of alpha. And for this D of alpha, you know, because alpha penalizes the distance, that it decreases with alpha. And we know from practice that the other terms increase. So it is not exactly increasing as in the regularization settings, but what we know is that the other terms are definitely bounded. So if we do not look at the solid curve, but on the dashed curve, which is an upper bound on this curve, then we can so extend the balancing principle from the regularization setting to the unsupervised domain adaptation setting by using all the mathematical tricks which are developed in inverse problems. Interestingly, also, we do not have to use exactly this kind of generalization bound. We can use any generalization bound, which is of the form of some distance plus some other terms which cannot be estimated. And there are a lot of such generalization bounds in literature. So basically what we come up is a procedure which allows to estimate the balancing value by using the tricks I showed you before. And there are some main properties of our approach. So first of all, it gives a model selection procedure which does not assume covariate shift, so that the source and target conditional distributions are the same, and it does not make the sample selection bias assumption. So in our case, the distributions can be even disjoint, which where we also have practical examples. The second property of our approach is the generality. So we can instantiate it by any generalization bound of the form D of alpha plus E of alpha. Also in the future, our model selection method can be used for generalization bounds, which will be presented in 5 years and which are maybe tighter and more interesting. And we have a theoretical guarantee, which I will not show you now in detail because of time, but it basically consists in the fact that we provide a constant which allows to bound the target error of the model selected by the balancing principle. So G alpha BP and this phi is the model which is chosen by our algorithm, which we propose. It satisfies a guarantee where we have a constant times the minimum alpha of D of alpha plus this, what is sometimes called in mathematics least non-decreasing majorant. So imagine this term E is increasing. Then on the right-hand side, you can see the bound. And our result shows that up to constant C, up to a constant factor C, our method minimizes the bound if E is increasing. And if this bound is tight, so let's assume in 10 years there will be a tight bound, then it shows that it computes the optimal model at an optimal error rate because this bound then computes the minimum. So anyways, if E is increasing, our method minimizes the bound at an optimal error rate. We also have empirical experiments, a lot of tables in the paper showing high performance. You can read the paper. I will not go into details of all the experiments now. Let me just conclude with our hope is that this criterion which sets a new step in a new direction for approaches with guarantees under different assumptions can help our community also beyond the problem of parameter choice. This is our hope. And I'm always open for new collaborations, and if Corona is over, for beer. And yeah, thank you very much.
Thank you very much, Werner. That was a really, really nice presentation and very, very good topic as well. This little graph of minimizing the error, I think I see it since, I don't know, 20 years or so. And we still not, we still didn't find how, like a good approach to reach the absolute number there. So very nice that it started to be standardized finally.
Thank you.
Thank you. Are there any questions to Werner, or should we move? Okay, so let's move to Kajetan.
Yes.
I hope I
you hear me?
pronounced your name properly.
Yeah, it's okay.
And thank you, Werner.
Where do you? Okay. Do you see my screen?
Yes.
Nice. Okay. Do you see the presentation?
No, not yet. Just
Okay.
we see the presentation itself, but not presented.
Yeah. Doesn't seem to be.
Yeah.
Okay. Maybe I try it again. Is there something? Okay. Well, I'm quite sorry for that. Maybe I restart my computer and we delay my talk to the next after the next talk.
Yeah, I was about to suggest the same.
Yeah.
So, Viktoriia, is it okay for you to be the next?
Yes, it is fine. Just wait 1 minute because I didn't open the presentation yet.
No problem. So in the meanwhile, I also say again, thank you to all of you for taking the time. I know also we are already a bit over time and you're probably all tired. But I really appreciate that you are here. I also hope that you're enjoying the NeurIPS that normally happens in the middle of the night for us here in Vienna.
Hi everyone, nice to see you here, and I hope that now we'll share my screen.
I think it doesn't yet.
Can you see it?
Oh, yes.
I will be presenting our article with my supervisor Robert Gagnon, The Complexity of Bayesian Network Learning, Revisiting the Superstructure. Our article is, just want to say in the beginning that it's theoretical, so we didn't make any experiments. We provided some algorithms for computing optimal Bayesian networks. So Bayesian networks are direct acyclic graphs that graphically represent dependencies between random variables. Probably all of you know. Vertices of this graph are variables, and arc means that the distribution of one variable depends on distribution of another. And once Bayesian network is constructed, it allows to infer distribution of dependent random variables based on values of independent ones. But in general case, constructing suitable Bayesian network is not an easy task, and we will restrict our attention to partial case of this problem, which can be formalized as follows. In input, we are given a set V of nodes For each node, we are given a local score function, and we have a total score L, which we want to achieve. And the question is whether there exists a directed acyclic graph on set of vertices V, such that sum of local scores evaluated in sets of neighbors of a vertex is at least L. We also will call this set of neighbors a parent set of a vertex. For example, consider this. We want to compute optimal Bayesian network on 3 vertices, which gives a score, not optimal, but which gives a score at least 5. And local scores are provided below. Then here is one of possible solutions. We add arcs from A and C to B, then local score of B is 3. Then we add arc from A to C, then parent set of C is A and local score of C is 3. And A has empty parent set, so local score of A is 0. So the total score is 6, which is greater than 5, so it is yes instance. We assume that local score functions are specified only where they are not equal to 0. For instance, in last example, this line where we have values in empty set are equal to 0 are not part of input. It's usually done to allow exponential blow up in size of input, because if we need to specify in every set value of function, it will be exponential in number of vertices. So this is a common way to store scoring functions, and it's called non-zero representation. And BNSL is known to be NP-hard in this non-zero representation. That's why researchers have studied problem from parameterized complexity viewpoint. Actually, to understand most of results, we need only one definition from parameterized complexity theory. It is when problem is called fixed parameter tractable. So problem is called fixed parameter tractable, or just FPT, when parameterized by parameter k, if it admits algorithm with running time some computable function of k times polynomial of n, where n is size of input. This allows to make a problem which is intractable from standard complexity viewpoint. Maybe it's NP-hard, for example, has running time 2 to the power n. It becomes tractable from parameterized complexity viewpoint because maybe we can distinguish some small part of input such that all blow up in complexity is localized in this part of input. Or it can be even not part of input, but some value which we assume that in real life it will be not very large. In our work, we will parameterize by structural properties of the superstructure graph. So we need to know what is the graph. To construct this graph, we start from vertex set V from input, and then for every pair of vertices, we add not-oriented edge between them. If there exists parent set of one vertex containing another one, and this parent set yields a non-zero score. And in last example, we had 3 vertices. At first, we see that vertex A has parent set containing B and C yielding non-zero score, so we add edges from A to B and from A to C. Then we see that B has a parent set AC yielding non-zero score, so we also need to add edge from B to C. So now it's not very interesting because we got just click on these vertices, but assume that we had one more vertex D with only parent set of non-zero score BC, then we would add edges from D to B and C, and there would be a superstructure graph. The intuition is that a superstructure graph captures any potential optimal network, so it makes a smaller search space for us. Parameterized complexity of BNSL with restriction on the superstructure graph was studied by Ordinac and Sider, who proved, in particular, that BNSL is not FPT if parameterized by the vertex cover number of the superstructure. But it's known that vertex cover number is very restrictive parameter. It's actually a minimum size of subset of vertices such that every edge has at least one endpoint in this set. So our question is, can we still identify structural properties of possibly high degree superstructures, which would make BNSL fixed parameter tractable? And we got 4 main results. Data reduction for BNSL parameterized by feedback edge number of the superstructure, fixed parameter algorithms for parameterization by new parameter called local feedback edge number. It is generalization of feedback edge number. W1 hardness for BNSL parameterized by the tree-cut width of the superstructure, and fixed parameter algorithms for BNSL in additive representation. So the first result is concerning data reduction for parameterization by feedback edge number. Feedback edge number of a graph is minimum size of edge set, such that deletion of these edges makes graph a forest. And we prove that there is data reduction algorithm which takes as input an instance of BNSL whose superstructure has feedback edge number at most k, runs in time polynomial in the input size, and outputs an equivalent instance of BNSL with number of nodes linear in k. In particular, this data reduction shows that BNSL is fixed parameter tractable when parameterized by feedback edge number, because we can at first run this reduction, then we have a network on at most k vertices, and then any algorithm we get to constructing an optimal network will of course depend, running time will of course depend only on k. But feedback edge number is a fairly restrictive parameter, so next question is maybe we can lift tractability to some less restrictive parameter. And here is a picture which shows why this parameter is really restrictive. Consider this graph. It has quite simple structure, but already feedback edge number is 8. We can take a black spanning tree, and there are still 8 red edges. But if we take a closer look at this picture, we see that, yes, there are a lot of feedback edges, but every vertex locally interacts only with 2 cycles. And we formalize it in our paper, what means local interacts with 2 cycles. Now I will not explain it because of lack of the time. But local feedback edge number of this graph will be 2, because every vertex locally interacts only with 2 cycles. And we show that BNSL is fixed parameter tractable when parameterized by this new parameter local feedback edge number of the superstructure. Next result is W1 hardness for tree-cut width. First, we show that this new parameter local feedback edge number is sandwiched between 2 known parameters, tree-cut width and feedback edge number. So tree-cut width is even less restrictive. And next question is, maybe we can even lift tractability to tree-cut width. However, we show that it is not the case. We show that BNSL is not FPT if parameterized by vertex cover number of the superstructure, even if all vertices outside of vertex cover are required to have degree at most 2, and this implies also hardness by tree-cut width. It's a picture of complexity which we now have. As you can see, W1 hardness holds for vertex cover number, which was showed by Ordinac and Sider, so it also holds for less restrictive parameters such as tree depth, path width, and tree width. We just established hardness for tree-cut width, and also got algorithms, fixed parameter tractable algorithms for local feedback edge number and data reduction for feedback edge number. And also we have a section where we consider some special representation of input, which of course it's possible not for every Bayesian network, but maybe for some of them, when local scoring functions are additive. And in this case, of course, always optimal solution would be achievable on complete graphs or tournaments, but it may lead to overfitting. To avoid this, we restrict number of parents by some constant q. And we show that this problem is NP hard for any q greater or equal than 3, FPT when parameterized by q plus the treewidth of the superstructure, but not FPT when parameterized by the treewidth of the superstructure alone. Our results complete picture of parameterized complexity of BNSL with respect to fundamental parameters. Maybe, or even we started to use this new parameter local feedback edge number in another graph theoretical problems. And of course, there are a lot of direction for the further research, for example, more efficient algorithms for computing the parameter, and some generalizations of additive representation, for example, for monotone scoring functions. That's it. Thank you for your attention.
Thank you very much, Viktoriia. That was very interesting.
Thank you. I'll try to stop sharing.
Thank you very much. I can already see that there could be a lot of real-world application for this, even when it's theoretical. So thank you very much for this. Do we have any questions? Okay, so if not, then thank you very much, Viktoriia. We will move to our last speaker, to Kajetan. I hope it works this time.
Thank you.
Let's cross fingers. Okay. You don't see any slide, don't you?
No, not yet.
Okay. Well, if it doesn't matter to you, because it doesn't seem that I can do it.
I think it's fine.
Yeah.
This way.
Okay.
Yeah.
So first of all, thank you for the invitation. Short disclaimer: we are actually the only paper that's not accepted to the main conference, but to 3 workshops actually. And this work was joined forces with Markus Hofmacher, Marius Konstantin-Dino, Philipp Renz, Angela Bitto-Nemling, Liam Patil, and Sepp Hochreiter, which are all at the LIT Institute of Machine Learning at JQ Linz. The paper I'm talking about is understanding the effects of dataset characteristics on offline reinforcement learning. So, first off, I would like shortly reintroduce what offline reinforcement learning is. I'm pretty sure every one of you knows, but to get the basics right. So reinforcement learning considers an agent represented by a policy that maps states to actions. So it's a function that's basically mapping states to actions. And it does so in order to interact with an environment. And the environment responds to this action the agent takes by transitioning the agent to a different state and giving it a scalar reward signal according to some usually unknown dynamics. And what we try to do in reinforcement learning with our algorithms is trying to find a policy that maximizes the cumulative reward signal over episodes of interactions, which is also called the return. And such a policy that, so to say, takes the optimal actions in order to get maximum return is called an optimal policy. Yes, the problem is when we apply reinforcement learning, we usually let the agent interact with the environment in an iterative cycle, so to say, and use the sample interactions to further improve the policy. This is problematic if we have real-world settings such as robotic manipulation or autonomous driving, where we can't risk to interact with the environment using a weak policy or a random policy, which we often use as an initial policy. A possible remedy for that is offline reinforcement learning, where we just consider a static data set to learn our policy from. This dataset is then, for instance, created by human experts or traditional methods, and is the only source of information the policy gets to learn a good policy. In this field of offline reinforcement learning, there have been a lot of algorithmic improvement over the past years, which aim to ameliorate the effects of the distribution shift between the static dataset and the environment during inference, because the policy that is learned from this dataset doesn't have to visit the same states and actions as the policy that created the dataset. However, there has been little work done to look into how the dataset influences, the dataset's characteristics influence how the policy is learned, basically. There has been a lot of work in this area, and one interesting work is this figure here from Gulcheri et al., where they show that different datasets lead to different performances of algorithms, where expert data leads to especially high performance of behavioral cloning, while noisy expert data leads to highest performance of their method regularized behavior value estimation. But what we are interested in from this figure is how actually this dataset composition influences which algorithm performs best on the environment afterwards. And it's not really clear, because the current state of affairs is that nominal descriptions, expert data and noisy expert data, instead of characterizable metrics, quantifiable metrics, are used to investigate this issue. Towards that end, our goal was to analyze the effect of dataset characteristics on algorithms applicable to the offline reinforcement learning setting. We investigated in order to do so, we investigated metrics to quantify reinforcement learning datasets characteristics, to get metrics that show us what behavior is contained in the datasets. Then we generated datasets using 5 different dataset generation schemes on a total of 6 environments from different domains. And finally, we used these datasets to evaluate popular algorithms used in the offline reinforcement learning setting to see how the different proposed algorithms perform on different dataset conditions. Okay, reinforcement learning datasets are very interesting because they have a special inner structure in it. They consist of tables of state, action, rewards that can be grouped as episodes, and the dataset consists of multiple of those episodes. While there are multiple options on how to characterize the behavior contained in such a dataset, such as the action or reward distribution, this work focuses on the trajectory quality and state action coverage to characterize which behavior is contained in the dataset. Trajectory quality means how well the behavioral policy, which created the dataset, performed during sampling of the dataset. And we measure it by the average episode return, or we would measure it by the average episode return compared to the maximum and minimal attainable returns giving the starting state. The state action coverage characterizes how much of the possible state action space the behavioral policy has visited during sampling. And we measure it by the unique state action pairs. And obviously we would calculate the fraction with the total number or the total size of the state action space. Unfortunately, we don't have access to the environment dynamics or the total size of the state action space. Therefore, we have to introduce some other metric to compare our trajectory quality and state action coverage of the dataset, the average episode return and the unique state action pairs too. For the trajectory quality, we use the average episode returns of a policy we obtained from applying a DeepQ network in an online standard, in a standard online reinforcement learning setting. And the average return of a random policy to get a normalized version to that. For the state action coverage, we use the state action pairs obtained from applying this online deep network. Like all intermediate state action pairs we got during the training. And what we do then is we quantify the data sets we obtained by means of this relative trajectory quality and relative state action coverage. And as one would easily see, state action coverage, for instance, is not indicative of what behavior is contained in the data set on its own. Because a policy can visit paths of the state action space that basically are not task related or not lead to any return, and can visit quite a lot of it, which basically adds nothing to learn from for the offline policy to get good behavior. Therefore, we contrast the relative trajectory quality and relative state action coverage to each other to characterize the data sets, as you can see on the figure on the right. All our experiments were performed on 6 different environments, ranging from coming from three different domains. The first is the classic control domain, the second the mini-grid domain, and the third the Minotaur domain. The reason behind why we use 3 different domains is that we have different environment dynamics, as well as very different state and action spaces, where we have even continuous action state spaces in the case of classic control. But this work was only performed on environments with discrete action spaces. Okay, now to the dataset generation. We generate the datasets using 5 different schemes that are used very often in the offline reinforcement learning literature. The first is the random policy, which is quite straightforward. The expert policy, which is the online policy trained by applying DQN in a standard online reinforcement learning setting, which we already used to normalize the trajectory quality. The mixed dataset, which is just a mixture of random and expert data. The replay dataset, which consists of all samples encountered throughout the online training of the online agent. And a noisy dataset, which is the expert, like the final online policy, but sampled epsilon greedy and dot greedy. These datasets down here show examples from the mountain car environment, where the position of points corresponds to the state, and the color of the points corresponds to the actions taken at the respective state. I'm not sure. Okay, goes on. If we use the 2 metrics we introduced beforehand, the relative trajectory quality and state action coverage, to characterize these 5 example datasets, we can see that the expert dataset has the highest trajectory quality, as one would expect, and the random dataset has the lowest, whereas the other 3 datasets have intermediate trajectory quality. But different levels of state action coverage, especially the noisy dataset, is better than the replay dataset even for this example. But obviously, we are not interested, or this was not the reason behind our work, to look into one environment, but to look into how this generally behaves. Therefore, these are the summary statistics for all environment and all datasets generated for these generation schemes. And we see basically the same, namely that the random and expert dataset attain the lowest and highest trajectory quality, whereas all other datasets have intermediate levels of trajectory quality. Quite similar, the relative state action coverage is quite high for all generation schemes except the expert scheme, which is obvious because expert policies only explore state action pairs that are on this optimal trajectory, so to say. There are some datasets that have higher state action coverage, which stem from the Minotaur games, which is quite interesting because all the others have quite low. And the reason for that is that the expert policy can explore, so to say, deeper into the game than the random data sets, and therefore get more different state action pairs. Okay, we tested our assumptions on a total of 9 different algorithms, which can be roughly divided into 3 categories. The first is the baseline category. The baseline learns basically the behavioral policy that created the data set, either directly in the case of behavioral cloning, which is just supervised cloning of, so to say, the supervised mapping of states to actions, or the action value in the case of behavior value estimation and Monte Carlo estimation. The off-policy algorithms are of the same family of the algorithms that were applied in the online setting to get this policy to compare the trajectory quality and state action coverage to. And these algorithms try to find an optimal policy. So they search unconstrained, usually in an MDP, they search unconstrained for an optimal policy. And they differ in how they approximate the action value, where DQN is just a point estimate, while quantum regression estimates the whole distribution, and random ensemble mixture is an ensemble of point estimates. And the distribution and the assembling have been shown to be more resilient, so to say, in the offline reinforcement learning setting. And finally, the policy constraint methods try to learn an optimal policy while staying close to the behavioral policy that created the data set. And in order to do so, batch constraint Q-learning enforces an explicit constraint, while conservative Q-learning regularizes the learned action values, and critic regularized regression performs basically filtered behavioral cloning. Okay, in the plot to the right, you see our main results. What do they show? Each of the subplots basically holds the same points, or the positions have the same points, which indicate the data sets we created. The color indicates the best performance we got when training the respective algorithm on this data set. The performance is again given by the normalized return compared to the online policy. Therefore, if we exceed 100, it means that we get a better policy than the online policy, so to say, which is quite interesting because that's the goal of offline, or the common benchmark in offline reinforcement learning, to exceed the online policy, or to exceed the policy we would obtain when directly interacting with the environment. Okay, we see that for behavioral cloning, we have a strong correlation with the relative trajectory quality of the data set, which is expected, as behavioral cloning is just a supervised imitation of the behavioral policy that created the data set. For behavior value estimation and Monte Carlo estimation, we see that they rely a lot on the specific dataset conditions, generally favoring datasets with highest state action coverage. But mostly, it's these datasets that lie on this line of 1 in the relative trajectory, relative state action coverage, which corresponds to the replay datasets. So behavior value estimation, Monte Carlo estimation work exceptionally well when applied on the replay dataset. For the off-policy methods that search unconstrained for an optimal policy, we see that we rely on high state action coverage to find good policies, which is obvious because, so to say, it takes the least assumptions in how to behave in this, or has the most information content to learn a good policy. Very interesting with respect to the literature is also that we didn't found that quantum regression DQN and random ensemble mixture outperform vanilla deep-Q network, which was shown to be the case on Atari games, with dataset settings similar to how we created the expert and the replay datasets. And finally, the policy constraint algorithms, they perform well basically across dataset conditions. So for datasets with low state action coverage, it basically is on par with behavioral cloning. And for datasets with higher state action coverage, they can utilize, so to say, the lookup for an optimal policy to exceed the simple imitation of behavioral cloning. So to summarize, we found that behavioral cloning is hard to beat for low state action coverage datasets. And searching for an optimal policy relies on high state action coverage to be successful. Finally, we found that policy constraint algorithms work well for most dataset conditions if datasets have at least high trajectory quality or state action coverage or both. Research directions for the future is to investigate other dataset metrics, for instance, the entropy of the behavioral policy that created the dataset. To expand this work to continuous action environments, which would necessitate different algorithms to cope with continuous action spaces. Well, then thank you for your attention, and I'm looking forward to your questions now.
Thank you very much, Kajetan. Actually, we do have one question from Hamid. Do you want to ask it yourself, or should I?
Sure. I think I asked this right before your slide, but just to make sure. So if you go to the slide where you were showing this normalization formula,
this one,
or the last one, it doesn't matter. So G is the average return on
yes.
an episode, right? Okay. And then the quality of the trajectory is based on this average return. So it's not some distance over trajectory space or anything. Everything is just based on the average return, right?
Yes, exactly. Yeah.
Okay.
So average return over data sets.
Right. Okay, that cleared up confusion.
And maybe I didn't explain it thoroughly. Like the idea of the trajectory quality would actually be to compare the return of the current, like the current return, looking at one episode, with the maximum attainable return and minimum attainable return, given the actual starting state. Actually, it's not average, but you like if you start in a maze, for instance, at the middle, you can and get -1 return reward for each step you take towards the exit. Then it's obviously better, or you can get higher, so to say, higher returns if you start more towards the exit, so to say. You would have to take that into account.
So they don't have to be similar in terms of trajectory. They just have to result in similar returns, and then they are close.
Exactly. Yeah.
Okay.
Exactly.
Got
exactly.
It. Got it. Thank you.
Yeah.
Thank you very much. I don't know if we have any other questions, but yeah, but if not, then thank you very much. It was really interesting. I admit it's been a while since I was playing with reinforcement learning, but I would like to try this method as well. I would like also to use this opportunity to thank you again for taking your time and presenting your research. And thank you also for the viewers on YouTube. I'm looking forward to see you again also on our next events, whether online and hopefully actually offline. And yeah, so thank you very much.
Okay. So thanks for organizing.